Dynamic programming is a method for solving complex problems by breaking them down into simpler, overlapping subproblems and storing solutions to these subproblems to avoid redundant computations. It can help you solve complex programming problems, such as those often seen in programming interview questions about data structures and algorithms. Alvin Zablin teaches this course about dynamic programming in Java. He has multiple super popular algorithm courses, and he is a great teacher.
Hey programmers, Alvin from Structy here. Welcome to our course on dynamic programming in Java. This is one of the most highly requested topics from freeCodeCamp students, so I'm super excited to explore this material with you in Java. So if you're looking for a really thorough exploration of dynamic programming exclusively in Java, you're in the right place. Of course, that means all of our code-specific walkthroughs are going to be in the Java programming language. As for the format of this course, we're going to build our dynamic programming knowledge by exploring a sequence of problems. The problems are going to start simple, but it's really going to give us the foundation we need to eventually solve some very tough dynamic programming problems in this very course. For every problem we work through, we're going to solve it using two steps. The first thing we're going to do is head to my whiteboard, where we'll come up with a strategy and really try to visualize the dynamic programming nature behind these problems. So after we draw things out on the whiteboard and get a really confident understanding of the structure behind a particular problem, then we're going to head into my editor, where we're actually going to code up a Java-specific solution. All right, so that's enough introduction for now. What I want to do is hop into our very first section on our exploration of dynamic programming. We're going to work through and frame our Fibonacci problem through a dynamic programming lens. Hey programmers, Alvin here. Right now I want to work through this fib problem. Of course, we're referring to the classic Fibonacci sequence. This is a really important, computer science problem, and to me it serves as the foundation to really unlocking a few harder concepts down the line. So even if you've done this fib problem before, it helps to review it together right now. We're going to see this core pattern show up a lot during the course together. And so let's start by understanding what we should do in this problem. Well, we know that the Fibonacci sequence has a few certain seed values. We say that the first number of the sequence is 0, and the second number of the sequence is 1. And then to generate further numbers of the sequence, we just take the sum of the previous two. In other words, I can take 0 plus 1, and that gives me the next number, 1, right? So the sequence starts 0, 1, 1. Then from there, I continue this pattern, right? I can take the 1 plus 1, that gives me 2. I can take the 1 plus 2, and of course that gives me 3, and so on and so forth. And of course I can generate the sequence of infinite length in this way. And so overall, in this rendition of Fibonacci, what we want to do is actually return the number at the specified index of the sequence, right? And so a really key insight about the Fibonacci sequence is to generate any particular number of the sequence, we must know some other numbers of the sequence, right? I can get 8 by just doing the previous 3 plus 5. If I wanted to actually formalize this problem a little bit better, what I'll have to do is understand that these numbers I have listed are really the elements of the sequence. And of course, I can assign some indices to those elements. So up top, I'll just label these increasing by 1, of course, but starting at 0. So I can say something like, hey, the 0th number of the sequence is 0, and the first number of the sequence is 1, and also the second number of the sequence is 1, and so on and so forth. So kind of jumping ahead a little bit. If I look at this particular position, what I see is, all right, it seems to be that the 7th number of the Fibonacci sequence is exactly 13. That's going to be overall the shape of this problem. All right, so how can we go about solving this one? And so for this particular approach, what I want us to do is actually work through this one recursively. I think the iterative solution is pretty straightforward, but I'm going to force us to solve this one recursively because it's going to help us learn some new topics along the way. So we'll kind of stick to a recursive mindset, and if you hate recursion, too bad, you'll learn to love it right now. And so looking at a particular example, let's say I wanted to figure out how I can come up with the solution for fib of 6. In other words, the 6th Fibonacci number is exactly 8. And so what I can start to do is figure out how to break down this problem. I know in general, to generate the 6th number of the sequence, I can take the 5th number and add that to the 4th number, right? It's exactly the rule of the Fibonacci sequence. Let me try to visualize this one a little bit better. So I'll represent the problem fib of 6 using somewhat of a tree, and I'll represent an instance of the problem as a node of this tree. So I have my top level problem of 6. That'll be the root of this tree. And this is a really important way to actually visualize recursion because it really shows us how we're going to utilize our return values and reconstruct our final answer. So if this is a new pattern for you, don't worry, we'll walk through it pretty slowly together. And so now that I have this root of 6, I have to figure out how do I break down this problem. Well, like we just said, to solve fib of 6, what I need to do is break that down into fib of 5. So that'll appear as a child of that 6 node. In the same way, fib of 4 also needs to be solved to solve our main problem over here. And notice how I have these, children nodes, of course, below the fib of 6, right? As I go downward in this tree, I should be getting smaller and smaller numbers in blue, right? That would represent a smaller problem. Because I know once I have a small enough input in blue, then I would have somewhat of a base case, kind of inherent to the Fibonacci sequence. So let's take a closer look at this 5 node over here, right? This node represents the problem of fib of 5, right? What is the 5th number of the sequence? And I know in general, my pattern is, all right, if I want to calculate fib of n, then I take the sum of n minus 1 and n minus 2. So I'm just going to apply that pattern to this 5 node. In other words, on 5's left, it's going to have a node of 4, and on 5's right, it's going to have a node of 3, right? Doing a minus 1 and minus 2 respectively. And it's a similar trend for the 4 node on the right-hand side over here, right? It's going to have 2 children, of course, doing minus 1 on the left and minus 2 on the right, giving 3 and 2 respectively. So let's keep applying this pattern. What we're going to do is fill out the next level of the tree until we can't fill it out anymore. What we have to notice here is when it comes to actually building the full tree, we have to stop at certain nodes. In other words, once I have an instance like 0 as my input to this little subproblem, I can't actually shrink that problem size any further. So I'll highlight all of these nodes whose input is 0, right? That represents the 0th number of the Fibonacci sequence. And something inherent in the problem is I can't really break that problem down any further. I know that for those particular nodes, they ought to return 0, right? Because the 0 number of the Fibonacci sequence is exactly 0. So in green, I'm going to represent the result or the answer to those subproblems, right? I'm going to put their answers above the problem itself. Right, so I'm trying to be very, very particular in my drawing. I'm always going to write a return value above a node here. And I have a similar case for all of my nodes who have an input of 1. Those are also a base case, right? Because the first number of the Fibonacci sequence is exactly 1. So we'll also fill in those 1s above. Cool. Now that I have some floating return values, I can start to reconstruct my larger problems at hand. So let's stay focused on the left-hand side of my tree. Let's look at this particular node. So I'm looking at this node of 2, and I have a left-hand value and a right-hand value ready to compute. I know that if I look at this node of 2, it's trying to figure out what's the second number of the Fibonacci sequence. And so at this node of 2 in blue, what I can do is just take the sum of its children, right, of those green values. So 1 plus 0 gives me 1. And if I do a quick sanity check, that must mean that the second number of the Fibonacci sequence is exactly 1. And this pattern continues up the tree, right? At this node of 3, I take the sum of the 1 plus 1, and I get 2. If I do a quick sanity check, that must mean the third number of the Fibonacci sequence is 2. What we're doing right now is really stepping through how a recursive code would actually return, right? Return means return to your caller, right? So return to your parent node. And so we'll fill in the rest of the values over here. And bear in mind, as you kind of draw out these diagrams, maybe for yourself, hopefully on pen and paper, or even on a whiteboard, it's really important, at least for me, that you check for correctness as you build the tree. So if you're in an interview, it really helps to not just check for your top level answer being correct, but at any points of your trace, you should have logical information. In other words, by just looking at this node, right, I have a blue node of 3 over here, whose return value is 2, that logically implies that the third Fibonacci number is 2. And that's totally correct, so I'm good to go for now, right? It would really be a drag if I kind of sketched through this entire drawing, only to realize I had a little typo or miscalculation somewhere below in the tree. So I highly recommend that you stay very aware of your subresults as you kind of trace through a diagram like this. So let's continue to build up these subsolutions. So I know that this node of 2 is going to take the sum of 1 plus 0. That gives me 1. Then finally, at the parent of 4, it's also going to take the sum. So 2 plus 1 is 3. And that must mean that the fourth Fibonacci number is, of course, 3. So let's speed this up a little bit for every other node in the tree. So we're going to add all of these up, so on and so forth. Now at the tippy top, we see that this node of 6 at the root is going to take the sum of 5 and 3. And of course, that gives me 8, which is exactly the punchline, right? The 6th Fibonacci number is indeed 8. And so looking at this pretty large tree, you might realize that, hey, our top level problem was asking for the 6th Fibonacci number, not a very large number in the sequence. However, we had to use a lot of nodes to actually represent that problem, how we broke it down. And that's something really important about this Fibonacci sequence, right? It has a pretty interesting complexity, a pretty large one at that. So let's try to analyze the complexity of this. We know that every node of this visual tree represents a recursive call. Right? And so the number of recursive calls I make over here, or the number of nodes of the tree, should roughly represent the time complexity of this solution. You're probably already recognizing that it's going to be a very, very large one. Let's go step by step over here. And so to analyze the complexity of recursion like this, I think it's really important to notice any patterns in the tree. To me, it's all about looking in the tree, right? I can kind of figure out at least the ballpark of the time complexity without even writing the code, right? Just using this visual. And so at first glance, you might notice that this one is pretty hard to analyze because the tree is asymmetric. In other words, notice that it's a little taller or deeper on the left-hand side, and then toward the right-hand side of the tree, it's actually much more shallow. And that kind of asymmetry makes us feel a little uncomfortable when it comes to figuring out any patterns. So here's what we'll do. Let's actually try to analyze this one by drawing an analogy. So let's ignore this exact Fibonacci tree right now and go for a more symmetric example. So let's say I had a similar recursive code that had a more symmetric recursion. So let's say I had some top level call with a value of 4. And let's say that this top level call to 4 actually made 2 more recursive calls, but both on a -1. In other words, the left child is the same as the right child, which is different from our classic Fibonacci, right? Fibonacci, our left was -1 and our right was -2. But now I'm just doing -1 on both sides. If I continue that pattern, that should give me a nice symmetric tree. Now let's say I had some base case roughly when my value is 1, so I can stop building the tree from here. And so this has a nice symmetry to it. Let's try to notice any patterns now. If I look at the different levels of this tree, let me look at how many nodes there are across a level. So for example, my very, very top level, and there's 1 node on that level. On the next level, there's 2 nodes, and then 4 nodes, and then 8 nodes. And you can probably see how this pattern scales, right? If I drew more of this tree, let's say I had a farther base case, it would be 16 nodes, and then 32 nodes, and so on. And so you probably realize the obvious pattern here, right? At the very top, at the root of my recursive tree, I have 1 node or 1 call, and then from one level to the next, I double it. I multiply by 2, right? And I do this process basically for every level of this tree. So that begs the question, how many levels are there in this tree? Well, just looking at this kind of particular concrete example, there's definitely about 4 levels, right? And I can kind of understand how to designate each level by just looking along this left-hand path, right? So colored in yellow, notice that I have 4, 3, 2, 1. That's just a decreasing pattern. So when it comes to the number of levels, it's pretty obvious to me that it's exactly n levels, right? If my top level problem at the root is where n equals 4, then I have, 4 levels, or in general, n levels. So it's pretty clear to me that when it comes to figuring out the total number of nodes in this tree, which implies the total number of recursive calls we make for this kind of toy problem, it looks like I would multiply 2 by itself n times over, which is a definition of an exponential 2 to the nth power. Cool. So maybe you're a little bit skeptical, and here's where we can either, really buy into kind of the big O complexity, or we can get bogged down by the finer details. Something that you might fall into sometimes, but you have to kind of be very aware of it, is big O is really just an estimate. So if you actually plug in some values here, you might notice, all right, if I did 2 to the 4th power, right, because 4 is my n in this particular example, that would be 16. And so if we actually counted the quantity of nodes in this visual tree, it would not be exactly 16. I'll label them over here starting at 1. There's actually going to be 15 nodes. So it's off a little bit. But if we, understand big O complexity, we know that if we have something that's of the shape of like 2 to the n minus 1, we can ignore the -1. And what's more is, even if it was off by like 5, right? If it's a -5, that's still a constant that we're subtracting. That still is dropped from the big O notation. So overall, I would consider this particular example as having O of the 2 to the n runtime, which would be exponential pretty slow, right? So while we're here, looking at this symmetric example before we hop back into fib, let's try to recognize what the space complexity is. We know that the space complexity for recursive code is going to be more or less the number of stack frames that we use, right, for our recursion. Because whenever we make a recursive call, that information has to be stored on the call stack, right? As we kind of make different function calls and also return from function calls. And so this is actually something I notice students have quite a difficult time analyzing. And so what I'm going to do is really trace through how we would make these recursive calls, as well as how to visualize the call stack, right? So this top level call of 4 would be added to the stack, right? So stack will be just a little rectangular block, right? And then as I make recursive calls, let's say now I call upon 3 as my input, that's also added to the stack. Notice that it's added on top of the 4, right? And really what we have to recognize here is every time we make a call, we're adding a new stack frame, and we only get to remove something from the call stack when it returns. So far, none of my calls have returned, right? Until I have 1 at the top of my stack. Right? At this point, I've kind of bottomed out at like a base case, so I can return from that call, which also means I remove it from the stack. At this point, I need to evaluate 2's right child, so I make another call to 1. And this process continues, right? Now I'm done with both of 2's calls, so it can return. Now I'm back at 3, but 3 has to call upon its right. And the same thing happens. What you'll notice at this point is, although there are many different stack frames we would have to eventually push onto the call stack, at any point in time, there's only about 4 different stack frames on the call stack, right? It's not as if that we store like all of these different stack frames simultaneously, right? It doesn't really make any sense. To add certain stack frames, you must have returned from other ones. So it's actually the case that the space complexity due to the call stack would just be O of n. Overall, we're looking at an exponential runtime and a linear space complexity. All right, so for this particular symmetric example, it has an exponential runtime and a linear space complexity, but how about for our actual Fibonacci tree? We know our Fibonacci tree is more lopsided. It's roughly going to be like half the size of that, and you can take my word for it, it would actually be the same big O complexity, right? Still 2 to the n, and then just an O of n space complexity. And so, kind of taking a lay of the land over here, the space complexity seems reasonable, right? However, whenever we have an exponential, usually that's not good enough. And there is actually a better or faster way to solve this one recursively, which is what I want to expose us to right now. So let's go back to the recursion tree for our fib problem, right? And so what we can do is try to recognize any patterns within this tree. Do you notice any duplicate work, right? And this is all about understanding, what this diagram represents, right? Every node I have drawn in here with its corresponding number represents a problem. And you can see I have many duplicate problems. So for example, if I look at this subtree, that subtree represents a subproblem, right? Rooted in 4. So I'm asking for the 4th Fibonacci number. Not only do I need to calculate that on the left-hand side of the tree, but at some other point down the line on the right-hand side, I need to calculate that same exact subproblem, right? These 2 subtrees are identical, and they both represent the same problem, the 4th Fibonacci number. And this pattern actually applies recursively because this strategy is recursive, right? So you can notice probably some other different duplicate subproblems, right? If I root myself at 3, I have to calculate this subtree 3 different times, right? And notice that 3 subtree is also internal to the fib of 4, so it's really duplicate. And there are a few other duplicate subtrees you can recognize over here. So we have a lot of duplicate work in this kind of brute force recursion. And if we actually store some subresults, then we can forego having to recalculate any of these subtrees down the line. And so really what we're looking to do is kind of prune out some branches of this tree to avoid some duplication. So what I'm going to do is kind of ignore this right-hand tree of 4. So I'm going to take that out because I would have calculated it on the left-hand side somewhere. And I'll do the same thing for this kind of middle tree of 3. So I can ignore that as well. Cool. Likewise for this too. And so at this point, we don't really have any full duplicate subtrees, right? I kind of took them out of my drawing. So if we actually store some results as we calculate these subproblems, this really represents all of the recursive calls that we'll have to make, right? And so you're wondering, how can I actually implement, that kind of pattern in my code? Well, it's all about just storing some additional information. So let's step through still fib of 6. So I want the 6th Fibonacci number. In the long run, we should get 8. And the strategy I'm introducing right now is called memoization. And so when it comes to implementing memoization in your language of choice, it's all about storing some additional data in a memo. And your memo is typically going to be your hashed data structure. So it could be like a hash map or a dictionary or object, depending on your weapon of choice here. Right? It's really important that I choose some data structure that gives me an O of 1 lookup time, right? So usually that would be your hashed data structures, whatever that is in your particular language. And so let's step through this one again, but now we're going to store some data inside of our memo. And so we have the same base cases as before, right? We know that the first Fibonacci number is 1 and the 0th Fibonacci number is 0. And when these values return to the parent of 2, we're still going to calculate the sum over here. So 1 plus 0 is just 1. But now that I have this result, I can store it in the memo. So I'm going to make the key represent the input to that node or that recursive call. And then its value is going to be that return value. And so if I look inside of my memo, it's a reminder that the second Fibonacci number is 1. So we'll continue this process. I know that I have a base case over here. It's still the case that the first Fibonacci number is 1, and I return to the parent. I calculate that, hey, the third Fibonacci number is 2, and I'm going to store that in my memo as well. And here's where things get a little more interesting. If I look at this node of 2 over here, I've actually calculated this subproblem before, right? And I can check that by just looking inside of my memo. My memo says, hey, the second Fibonacci number is 1, so without having to recurse and build the full subtree once again, I'll just go ahead and fetch the stored value in my memo. So I'm just going to jot down a 1 above this node of 2. And I can return to my parent, and I figure out that, hey, the fourth Fibonacci number is 3. And of course, I want to be sure to return that, but also store it in my memo for the future. And same thing happens at this 3 node, right? This 3 node is, again, in my memo. So without, recursing through my tree, I'm going to just fetch that value from my memo. Right? I already know that, hey, the third Fibonacci number is 2. And so I can calculate the value at my parent, right? Fifth Fibonacci number is 5. Be sure to store that in your memo, and so on and so forth. By the time we get to the very top of our tree, of course, we have the fact that the 6th Fibonacci number is indeed 8. And I avoided a lot of the duplicate recursive calls. So it's clear to me that we avoid a lot of duplicate work, but what exactly is the runtime now, right? And so we'll try to notice some patterns. So this visual tree represents our Fibonacci recursion after we implement this memoization strategy, right? I'll try to generalize it over here. So I'll kind of tidy up these edges over here. And let's say I increased the size of this problem. So instead of fib of 6, what if I asked you for fib of 7? That recursion tree would look something like this, right? Notice that the root is now 7, of course, and it's still the case that the left child is -1, so a 6, and the right child of the 7 is a -2, or a 5, right? Still obeying the rules of Fibonacci. And I only added 2 more nodes. If I increase the problem size to fib of 8, I would still add 2 more nodes. So every time I increase my input by 1, I only add 2 nodes. It's always adding a constant number of nodes. At this point, our problem scales linearly, right? In general, we're going to notice that we have basically 2 times n nodes. And notice that that's not 2 to the n, right? I'm saying 2 times n. And so we can simplify that to a runtime of O of n. And the space complexity is still the same, right? Notice that the space complexity for this algorithm is really just going to be the height of the visual tree. It still looks like a linear chain, right? If I go along the left-hand path, it just goes 8, 7, 6, 5, 4, and so on. So definitely an O of n space complexity. And this is actually a pretty efficient solution for our Fibonacci. And so I think from this point, let's go ahead and implement this in some code. That way we can have this core pattern under our belts. So I highly recommend that you try to implement this one in some code on your own. But don't forget, we also have the video walkthrough available if you get stuck or just want to code along. Now that we're done sketching out a strategy for this problem on the whiteboard, what you want to do is follow the link in the description for this fib problem so you can follow along and code up our solution in Java with me. Hey programmers, Alvin here. What I want to do right now is go over the Java walkthrough for this fib problem. So this is going to be our very first problem in the dynamic programming section. And the way I'm going to teach you to solve dynamic programming problems is using recursion plus memoization. So we're going to start just by warming up here and solving this Fibonacci problem using recursion, and then we're going to apply our memoization strategy on top of it. And this is going to be a really great strategy that can scale to a lot of different dynamic programming problems. Obviously, you might be thinking that you could solve a Fibonacci using some, pretty classic iterative code, and you definitely can. However, I'm going to show you how to solve this recursively with memoization because it's really going to set you up for harder problems later on. And so let's jump right in. When it comes to setting up the recursive code here, I want to start with my base cases. And they tell us that the 0th number of the Fibonacci sequence is 0, and the first number of the Fibonacci sequence is 1. So I'll turn those into base cases. So I can just go ahead and check, hey, if n equals 0, then I know I need to return 0. Likewise, if n is equal to 1, I know I want to return 1. So to kind of combine those into a single base case here, I can check if n equals 0 or n equals 1, we'll just return n itself, right? Because the 0th number of the sequence is 0 and the first number of the sequence is 1. And that'll give me my 2 base cases to start. Then from there, I only need one more line of code. The recursive definition of Fibonacci is to get some further a number of the sequence, you just take the sum of the previous 2. Right? So I know that the previous number of the sequence would be Fibonacci of n minus 1, right? Because n represents the number I'm asking for. So the number in the sequence that comes before would be n minus 1. And I want to add that to Fibonacci of n minus 2, right? So that would be the number 2 steps ago, right? I take the sum of them, and that would give me my current number. So let's give that a test run. This will be correct, but it won't scale in terms of the time complexity. Like we said in the approach video, the time complexity of this Fibonacci function, although it's very short code, is exponential, right? It's 2 to the n. And so the growth of this function as we increase the input number n is very, very large. So you're actually going to get a timeout for this one. And so to make this faster, we're going to layer on a memoization strategy, right? And so what's really important in the way I teach memoization is we always start by solving the brute force. And here I have the brute force, right? I can identify that I've correctly implemented the brute force when I get correct results for my method, except it's slow, right? So it times out for some very large input. For example, if I take a look at the test case I'm failing right now, it would be calling Fibonacci with an n of 46, right? It would give me some large value, and because this has an exponential time complexity, that's far too large for me to wait around for. And so when it comes to creating a memoization around this brute force solution, in Java, what I usually do is create 2 separate methods. I'll have my main method, and I'll also have my recursive helper method that also takes in a memo. And so let me create another version of this method above. That would be the main method. And it's just going to really call and pass control into my recursive method. I'm going to overload it with an additional argument here, right? So fib, the recursive method, is going to take in not only the integer n, but my memo. And for you in Java, it'd be nice if you implement your memo using a fast lookup data structure, right? Because you want to improve the runtime of this code. So you want to store your subresults in a fast lookup data structure. So for you, that could be as simple as a hash map. So I'm going to import up top Java util hash map. Because I know that a hash map has O of 1 insertion and O of 1 lookup. And I'll take in a hash map over here. And when it comes to how I design the structure of the hash map, I know that the keys of my hash map need to be input arguments to my method here, right? So I know the input argument is a number or integer n, so I'm going to make the key integer. I make the corresponding value in the hash map the return value for my method. It's going to have integer values as well. I'll just call this argument memo. So that means when I, in my main function, call my recursive method here, I'll pass in the original n, but I'll give it a new hash map. Nice. I can just return whatever the recursive method returns. So do bear in mind that this recursive method now in line 9 is taking in my original argument n as well as this memo hash map, right? And this memo hash map is going to be shared for the entire recursion, right? So what I need to be sure to do is I'm taking in the memo, that's an argument here. When I call recursively on fib, I want to pass along the same memo. Right, you're passing it by reference, so you can have all of your recursive calls share the same memo object. right? Think of it as if when you visualize like the recursion tree, like we did in our approach video, you want all of your nodes in the tree to refer to the same memo. Awesome. So that's just me adding an additional argument into fib, but now I actually want to use that memo object. And so what you should do is check if your argument is already a key in your memo, right? So I'm going to check it over here. It kind of acts like another base case here, so I put it at the top. So I'm going to check if my memo already contains the key of my argument n, right? What I can do is then just return the stored value of that key. So I can do memo.get n. Obviously, this only works if I, over time store values into my memo, which I'll do in a moment, right? So I know my memo is going to map, right, arguments of my method to their return values. So if I find an argument in the memo that matches my current argument, I'm just going to return its stored value in the memo. But that means I need to be storing things over time into the memo. And so now you should locate wherever you return recursively for your method. So that'd be the line 19 return, right? Those are my recursive return values, right? I know that line 11 is not a recursive return value because it's literally my base case, right? So I know that this value here, I know it's really composed of, two separate recursive calls, but I know that this will ultimately evaluate to a number, right? I'm returning a number here. That number is like the answer. So what I'll do is I'll save it in a variable. I'll just call it result. And I know that this result is going to be the answer for Fibonacci of n. So what I want to do is in my memo, before I leave, I want to store using the key of n. I want to make the corresponding value this result. Again, what I'm doing here is I'm making sure my memo maps arguments of my method to their return values. I know the answer for like fib of n is this result. And what you want to be sure to do is just complete the return value like before. So I just want to return result. So I'm still returning the same data as before. I'm just additionally storing it into a memo for later on. And what's great is later on, somewhere in your recursion, when you encounter an n that you've seen before, I mean, that's going to happen in this problem because we, demoed it in the approach video. When you see an input and you want to evaluate an input n that you've seen before, then you'll actually hit this base case on line 14. You're going to find that that argument is already in the memo, and you're just going to return the stored value inside. And that happens in constant time, right? Because I know getting from a hash map is constant time. And so with that change, let's go ahead and give this a test run. Really important thing to remember to do is be sure to pass your memo, to your recursive calls over here. That way you get that shared information across all of your recursive calls. Awesome, and there we have it. So by implementing this memoization strategy on top of our brute force, we really improve the time complexity of this solution, right? Like we said in the approach video, now we're looking at an O of n runtime. Right? Space complexity is also going to be O of n because we have to store all of these calls on the call stack. And even if we consider the size of our memo, we know that our memo is just going to have a number of entries that could be at most equal to our input n, right? Because I'm using my input n as the keys of my hash map, and I know that keys are unique. All right, programmers, so what I want you to do is take a moment, really be sure to redo this problem and understand how we solved it in two steps, right? First, I solved just the brute force recursion, and then I apply my memoization on top of it. This is going to be a really, really important pattern moving forward. We're going to scale it to solve some pretty interesting and difficult dynamic programming problems, but it always follows this core pattern of solving a brute force recursion, then additionally adding a memo hash map to it. And we'll do a variation of this in the next video. I'll see you there. Hey programmers, Alvin here. Right now I want to show you the approach for this Tribonacci problem. And so I know you're thinking, why is he having us do basically a ripoff of Fibonacci? Well, I think it's really important that if you want to get good at these algorithm things, then you have to have a certain level of repetition. As the saying goes, one is none, right? So even though, we've just done the Fibonacci problem, doesn't mean that it's completely something that we've mastered. So if anything, this should be a quick little review, right? Of course, I want you to solve this Tribonacci problem recursively. And so let's take a look at the sequence. So here is a few numbers of the Tribonacci sequence. What you'll notice is in this particular problem, like before, I want you to give me back a particular number of the sequence. So imagine that we had corresponding indices for each of these numbers. When it comes to the Tribonacci sequence, we're going to have 3 separate base cases, right? The 0th number of the sequence is 0, and also the first number of the sequence is 0, and the second number of the sequence is 1. So with those 3 seed values, we can come up with our general rule. Right? Just like before, to calculate a number of the sequence or the next number of the sequence, you just take the sum of the previous 3 numbers, right? Or in general, to calculate trib of n, you do the sum of n minus 1, n minus 2, and n minus 3, and there you'll have your final answer. Right? So kind of jumping at a particular spot within the sequence, if I took the sum of 4 plus 7 plus 13, that would give me exactly 24. So you should feel right at home in this particular problem. And so let's start to draw this one out. I don't want to skip any steps. And so before we start building this one, let's have some foresight and figure out how to visualize a problem like this, right? And what's great about visualizing it is that at least if we spend some time, sketching out, a structure of the problem, like visually, it can also help us figure out the complexity of this particular problem. So right now I want to step through calculating the 5th number of the sequence, which should be 4 in the long run. So like before, I'm going to represent an instance of this problem just with a tree. And so my top level problem will be the root of this tree, right? I want to find trib of 5. And I know that I have to break this problem down into 3 subproblems, right? In other words, I can generate 3 children by doing a -1, -2, and -3, respectively. And I'm just going to carry over that pattern for as many nodes as I can. And of course, whenever I hit like a base case, I can't break that node down any further. We know that when it comes to our Tribonacci problem, we have 3 separate base cases, right? Representing these particular return values. So I'm just going to plug in these subresults. So I should have all of these calculated values, right? 0th number is 0, first number is 0, and also the second number is 1. Now I can start reconstructing my sub-solutions, right? So if I take a look at the particular, to the left, the 3 node, I take the sum of its 3 children, 1 plus 0 gives me 1, right? So the third Fibonacci number is 1. And I'll just continue this pattern, right? Every parent node just takes the sum of its 3 children return values. So I get values that look like this. And finally at the root, I just take the sum of 2 plus 1 plus 1, which gives me a final answer of 4, right? Very similar to our classic fib problem. So this would be a working solution, basically just doing the same recursive code, except we're going to have 3 recursive calls, which makes sense because every call we make corresponds to a branch that we have in this visual tree. However, what's the complexity of this one? It's pretty slow for the same reasons our Fibonacci code was slow before, right? So if you take a look at this particular tree, I can derive the time complexity of it. So I know that for my recursive code, the time complexity is at least going to be the number of recursive calls that I make. And if every recursive call corresponds to a node of this tree, I have to figure out what the long-term pattern for the number of nodes is in this recursion tree. So I know that the height of this tree is pretty obvious. It looks like it's going to be along the order of n. And how do I know that? Well, if you look along the left-hand path, it just goes 5, 4, 3, 2. And in general, that's roughly n things, right? Now I'll just think about how many nodes are across on every level. At the top level, there's 1 node. And to get to the next level, I multiply it by 3. And I continue this pattern, right? As a tree gets bigger and bigger, from one level to the next, I would continue by tripling the number of nodes, right? Very similar to our Fibonacci problem. And so you guessed it, the complexity of this is 3 to the n. So an exponential, but with a base of 3, right? And it is the case that our space complexity is a pretty reasonable O of n, right? Of course, we're referring to the space complexity due to the call stack, right? And in general, we can figure out the space complexity from the call stack if we draw out the tree, and we can just look at the height of the tree. The height of the tree being basically the number of levels. And there's roughly, 4 levels here. So I guess it's off by 1, even though our input was 5, right? And so to make this one a little faster, of course, we can just notice any duplicate subproblems, right? So same story like we're used to. Take a look at this subtree, rooted in 3, and I have this subtree appearing here as well. And so I want to avoid resolving that subproblem. We're going to use the same strategy as before, but this time I want to use a different word to describe it. Really what we're utilizing here is dynamic programming. So dynamic programming is really a type of problem solving where we utilize any overlapping subproblems, right? In other words, I have this subproblem of calculating the third Tribonacci number, and if I can store that information the first time I solve that problem, I can utilize it later on because I'm probably going to encounter that same subproblem. Right, so this is in the family of dynamic programming strategies. And so far, we've been working with memoization. So really, memoization is just one way we can implement dynamic programming. And so if we use dynamic programming wisely, we should be able to forego that duplicate subtree, right? And overall, we'd be looking at an O of n runtime and O of n space complexity if we implemented that correctly, right? And so to implement that, of course, we're going to use some hash data structure to build that memo. So for my Python people, you're going to use like a dictionary. For my JavaScript people, you're going to use an object. For my Java people, going to use a hash map, right? Any fast lookup data structure. And at this point, we have a pretty optimal solution for this Tribonacci sequence, right? It should be able to run in a pretty decent time. And so with that, what I want you to do is give this code a shot on your own. But don't forget, if you get stuck, we do have a code walkthrough available as well. So give it a go. Now that we're done sketching out this Tribonacci problem on our whiteboard, what you want to do is head down to the links in the description and click on the Tribonacci link. That way you can follow along and code up the Java solution with me. Hey programmers, welcome back. Right now I want to go over the Java walkthrough for this Tribonacci problem. So it's going to be another dynamic programming problem just to kind of ease us into the core pattern that I'm trying to teach you guys in this course, and that'll help you solve almost any dynamic programming problem. And so this is going to be a variation off of Fibonacci. It's just called Tribonacci. It's really the same pattern, except to generate a further number of the sequence, you need to use the sum of the previous three numbers. And here I'll start with my base cases, right? I know the Tribonacci sequence has some different seed values. We see that the 0th and first numbers are both 0. Right, so I'm going to actually just go ahead and jump right in here. I'll start with that as my base case. I'm going to solve this one for now with a brute force recursion. So I'm going to check, hey, if my n is 0 or my n is 1, well, the 0 and 1 elements of the sequence are both 0, so I return 0 in either case. Then additionally, I need another base case. If n is 2, I return the number 1. Really just arbitrary values for the sequence here. So if n equals 2, and return the value of 1. And those would be my two base cases. When it comes to creating the recursive case here, you just take the sum of the last three numbers of the sequence. So for me, that's as simple as I take the Tribonacci of n minus 1, and I add that to Tribonacci of n minus 2, and also add it to Tribonacci of n minus 3. Cool, so let's give that a test run. This is a really important step. Never ever skip it, right? Whenever you're solving a dynamic programming problem using memoization, you ought to solve it brute force first and verify that your code is correct. For me, correct means that I always get a correct result for my method, right? A timeout is okay, right? Eventually, if we had more time to use up here, you would be able to pass test case 07. You will get the correct answer, but this code is just far too slow as it is. Right? So now that I verify that, okay, this code is just a matter of speed, right? It's just slow, I can add memoization on top of it. So just like before, for you in Java, I think the best way to solve this one, the structure of code, is to overload this method. And your recursive method, your brute force, is now going to take in a new argument. It's going to be a hash map. And when it comes to how I set up the keys and values, keys are going to be the arguments to your method. Here I just have a single argument n, so I'll make that an integer key. The corresponding return value is going to also be an integer, so it's going to have integer value. I like to call it memo. Awesome. From there, in my main method, you just want to delegate to your recursive helper, and you should pass in, a new hash map instance here. So at the top, I should import the right thing here. So I'll import Java util hash map, and you can pass it in inline. Be sure to instantiate it here. So new hash map. Awesome. And now when it comes to my recipe for memoization, I have the brute force. I'll start by adding a base case that checks if my key or if my input argument is already in the memo. So I'll add over here along my base cases. And I'll say if my memo contains the key of n. Right? And if it's there, that means I would have also stored the value that is the answer for that input n. I'm just going to return whatever that stored answer, that stored value is. So I'll do memo.get n in that case. Awesome. So I have the logic that looks into my memo, like my memo fetching logic. Now I need my memo insertion logic, right? So now I need to locate my recursive return value, right? This is where I return the final answer for n, right? This would be a number technically. I'm going to store it to a variable. I'll call it result. And before I leave and return the result, I actually want to store that result into my memo. So I actually do memo.put. And you should always use the key that's your current input argument, right? So this result is the answer for Tribonacci of n, right? Because I'm returning it for a call to n. And so n is going to be my key here, right? So I'll do n, I'll make the value the result. A very important design choice that we make when we solve our memoization this way is we're only going to memoize our current call, right? So in other words, all of my memo keying happens with the argument n, right? I check if it contains n, and if it doesn't, then I put a new key of n. I don't write any like awkward, heavy-handed logic, like doing memo.put, and I try to cache like n-1 with some sub-result, right? That gets very, very messy, right? Because we're solving this recursively, if we handle all of the memoization for our argument n, then everything else will actually be memoized as well, right? Because you know that for this particular call, when we jump in and evaluate that call recursively, this n-1, whatever actual number that is an n in some other frame of reference, right? So you're only going to want to memoize, to keep your code very clean, just your current argument n, right? Don't try to do any of like the sub problems with the children here. Awesome. And one final thing to do, if I actually test this, it's a very common mistake, it won't actually be any faster. That's because these calls to Tribonacci, in my recursive case, they need to actually refer to my overloaded method here, which takes in my memo. Obviously, I want to share this memo hash map for the entire recursion tree here. So I'm going to add that into the mix, just pass along the memo. And that should do the trick. Awesome, and there we have it. Hey programmers, Alvin here. Right now, let's go over the approach for this sum possible problem. So in this problem, we want to take in two arguments. We're going to be given a amount as well as an array filled with numbers. What we want to do is return true or false, indicating whether or not we can use some numbers of the array to generate the amount by adding them together. In this particular example, I should return true because I can totally make 5 by adding up some numbers in the array. There are a few different ways to do that. I could have done 2 plus 3, or 3 plus 1 plus 1, or also 2 plus 1 plus 2, and there are actually a whole bunch of other different ways you can sum up to 5. But since I have at least one way to generate 5, I'm going to return true. So overall, we're just looking for a Boolean return type for our function here. It could be the case that based on the inputs we're given, it might not be possible. So if I gave you a target amount of 15, and I gave you numbers to choose from like 6, 4, and 10, that would actually be impossible. So you should return false. All right, so how do we start attacking this one? We'll step through an example where we want to generate a target amount of 4, and we have numbers 1, 2, and 3. This should be a sufficiently large example to step through. Here my intuition tells me that smaller amounts are easier to calculate than larger amounts. So what I can do is try to shrink my amount as much as possible until I get to a trivially small amount for which I know the answer for. So let's say I start with my amount of 4. What options do I have here? Well, if I think about my first choice, what I could do is take a 1. So this 1 is going to represent the first number I can choose, right? And what I can do from there is actually subtract that 1 from the 4. That would give me a new amount of 3. But still at the 4 node over there, what I can do is also maybe consider taking a 2. If I do 4 minus 2, then my next amount is 2. And the final option would be taking a 3. If I do 4 minus 3, that'd give me 1. And at this point, I'm starting to shrink my problem size. So inside of the nodes in blue, we're going to have listed the amount that we're trying to break down. And then the numbers in yellow on the edges represent the choice of numbers that we choose. And we're starting to shrink our problem size. So let's say we take a look at the 3 node on the left. We can break it down further, right, using my options of 1, 2, and 3, and that would yield 2, 1, and 0, respectively. If I take a look at this 2 node over here in the middle, I have to watch out, because I can only use some of my numbers for valid moves, right? In other words, I can do 2 minus 1 or 2 minus 2, and that'll give me 1 and 0 respectively. But what I should not do is 2 minus 3, right? Although I have a third option of doing a 3, that would be too large right now, and that would actually bring me to a negative quantity. So we're going to need to watch out for that in our drawing, as well as when we implement the code. Similarly, for this right-hand node of 1, I can only subtract 1 for it, because using any of the other numbers would bring me to a negative quantity. So we'll continue this pattern for all of our nodes until we can't break them down any further. And this would be the complete tree. Really what we're describing is the decision tree for all of the options that we can possibly make. Right? So although I'm saying tree here, I'm really referring to the fact that we're breaking this problem down recursively. When we go ahead and implement this, we're not going to have to build any like tree data structure, but we're going to solve it using recursion, right? I use this tree as a way to actually understand all of the options I can take. So since we know that this tree visualizes the recursion, where can we locate the base case? Well, that would really be just the leaves of this tree. What we can do is recognize that we have a bunch of 0 nodes over here, and to me that would be a trivially small amount that I can always know the answer for. So that's going to be my base case, right? In other words, if someone gave me an amount of 0, I'm just going to return true. Why does that make sense? Well, I can always generate 0 by just taking no elements of the numbers array. And I can always return true regardless of what numbers you give me. You can even give me no numbers and that'd be totally fine. I can still generate 0 by taking none of those numbers. And so what I'll do is jot down this return value above all of my 0 nodes. Those are going to be my base cases, right? My base case calls. And I know that if I see a single true anywhere in the tree, then it should be possible to generate the amount. Obviously here we can't really go wrong, and we have a lot of different ways to generate the amount. If you look within this tree, not only do you know that there are a bunch of different ways to make our amount of 4, but you can actually see what numbers you added to generate that amount. For example, if I look at this path, this represents doing a 1 plus 2 plus 1 to generate 4, right? I'm just adding the numbers that I have along the edges here. So this tree tells you a lot of information, and you can use it to solve a bunch of different variations of this problem. So now let's start to look at how the values return here. So given a parent node, if it receives a true from any of its children, then it's also going to return true. So that would evaluate something like this. Until we get a true at the top as our final answer. So far we've described the brute force way to calculate the answer here, and I think it's worth going through the complexity. So here I have 2 arguments to my function. If we say that a is the amount and n is the length of numbers, we can say that the time complexity is going to be n to the a power. So this is going to be exponential. So what we're doing here is putting n in the base of the exponent because we know given a node, it's going to give at most n children because I have to branch for every option of number in the numbers array. And I'm putting a in the exponent because I know that the height of the tree is at worst going to be a. You can easily see that in this particular example. If you start at the root and just keep going to the left, it goes 4, 3, 2, 1, 0, which would mean that the height of the tree, in the worst case, is exactly a if I had to keep subtracting 1 from my node. So overall, I'm looking at an n to the a complexity, which is an exponential and typically going to be too large to actually run for reasonably large inputs. We talk about the space complexity. It's just going to be O of a right now based on the height of our tree, right? We know the height of the visual tree would give us the maximal stack depth. So how can we do better? Well, you should probably catch the drift by now. Take a look at this tree and notice if you see any duplicate work. What I can notice here is I have some duplicate subtrees, right? I can see these subtrees rooted in 2 that are identical, and I even have smaller subtrees that are the same, like the ones rooted in 1. And I know that if I have duplicate subtrees in this visual, that means I'm trying to solve duplicate problems, right? If someone asks me, is it possible to generate 2 for the first time, then later on, if someone asks me again, I should have just memorized that answer. Right? And so here we're going to use that memoization strategy. Just store some solutions in some cache, that way I can fetch them later on. If you implemented memoization like we've seen previously, then you would be able to trim out some branches of this tree, ending up with this smaller structure. What would this memoized complexity be? Well, we'll still say that a is the amount and n is the length of numbers. What we did was actually remove the exponential nature of this problem now. We'll say that the time complexity is O of a times n. So it's no longer an exponent, I'm simply multiplying them, right? So a still represents the number of levels within my tree, right? The height of the tree. And then n represents the width of my tree, right? For every level, I will have at most n nodes. And it would still be the case that our space complexity is O of a. We would still use a stack frames on our call stack due to the recursion. And in terms of storing our memo, we know that's also going to be linear in a. And when it comes to the hash map we use to store our memo, the space complexity for that is still going to be O of a, because we're just going to use every possible amount as a key of that memo. Before I let you go, let's step through an amount that would not be possible given some numbers. So we'll step through a scenario that should return false. So my amount is 15, and I have numbers of 4, 6, and 10. If we attack this one the same way, we'll start with 15 in the root, and we'll subtract each option of number. giving us 11, 9, and 5. And I'm going to carry this over as much as I can until I can't reduce my amount anymore. So the full tree will look like this. The nodes highlighted in red are the nodes that I can't break down any further because it would bring me to a negative quantity. So if I have any remaining quantities in those red nodes, then I know that that would mean those quantities are not possible to be generated. So those should be a base case that return false. And now I can evaluate my returns in the same way as usual, right? I just bubble these up to their parents. A parent is going to return true only if one of its children calls also return true. But everyone here is false, so I'll get false all the way back up the tree. All right, programmers, I think that's all I got for this approach video. What you want to do is possibly give this one a shot on your own. See if you can translate our visual diagrams into some code. And then if you get stuck, you can find me in the walkthrough videos. I'll see you there. Now that we're done drawing up our sum possible solution, what you want to do is head down to the links in the description below where you can find the link to the sum possible problem, because we're going to code up the Java solution right now together. Hey programmers, Alvin from Structy here. What I want to do is go over the Java walkthrough for the sum possible problem. So you definitely want to make sure you watch the approach video for this one. This is going to be what I consider like our first actually difficult dynamic programming problem. And so those previous toy problems of like fib and Tribonacci, those have all been building up to a problem like this, right? What I really want to emphasize as we kind of write the code for this is try to compare the process for solving it similar to how we solved Fibonacci and Tribonacci, right? Meaning that we're going to start by solving just some brute force recursion, check that it works, check that it's correct. It's probably going to be too slow. And then we add our memoization on top of it, right? We're going to scale out this solution here. And so let's jump right in. And so to solve this one, I know I need a brute force recursion. And with any recursion, I like to think about my base cases, right? So when it comes to my base cases, I have to think about, all right, what are some trivially small inputs for which I automatically know the answer. And like we said in the approach video, the great base case here is going to be if your amount is really small. So if my amount is 0. If your amount is 0, then what you want to do is kind of give back a Boolean representing, all right, is it possible to add up numbers such that their sum is 0? And that's always possible, right? You can always get a sum of 0 by adding no numbers together, right? That's trivially true. And so I'm going to return true here. So if you hit an amount of 0, just return true. Awesome. But from there, I know I have some positive amount, and I need to break it down smaller and smaller toward this base case. And I know that to shrink the amount, I must subtract some value from the numbers list. So I'm going to start iterating through the possibilities here. So I'm going to iterate through every int, we'll say num within the numbers list. And I know that I'm going to take my current amount and subtract it by this number. And so just for some clarity here, I'm going to label this variable as my sub amount, right? Because it's my original amount just with some number reduced out of it. Awesome. And now what I want to do is keep solving this problem recursively. So now I want to figure out, is it possible to have a sum that adds up to this sub amount? And I have a method to do that. It's the current method I'm writing, right? So I'm going to call sum possible and check if the sub amount is possible. Right? The second argument to this recursive method should be the same argument, right? Numbers. You can reuse the numbers as much as you want, so I can pass in the same numbers. Awesome. But now recursively I have to think about, all right, what does this give back? Well, I know that it definitely gives back a Boolean, and that Boolean represents whether or not it's possible to create the sub amount, right? If it is possible, so if this comes back as true, then I know that it must be possible to sum up to the entire full amount. So I'm going to return true here. And why does that logically make sense? Well, if it's possible to make my sub amount, right, it must also be possible to make my full amount, because to make my full amount, I can just add one additional number to it, right? Because to get the sub amount in the first place, I took out one valid choice of number. But on the flip side, if it's not possible, so if this a recursive call returns false, then you want to keep looking and consider if another choice of number would be possible, right? So something to watch out for here is you don't want to write like a else return false, right? Because you would exit too early, right? You only want to return true if you find a valid amount, right? The place you should return false is only after you're done checking every possible amount and you don't find one, right? So you want to write a late return false here, right? If I don't find any sub amount that's possible, and I checked all of them, so after my for loop, then you can return false. Hey, it must not be possible to create my amount. Awesome. So this looks like my brute force solution, but we are missing one kind of glaring case. We'll want to pay special attention to our subtraction on line 10, right? Based on what our amount and number is, we could get like a negative value for subamount. Imagine my amount is 2 and maybe my number is 5. Well, if I do 2 minus 5, I get -3, and things will get kind of nasty from there. Because at that point, I've already overshot my base case of 0, and so you'd get increasingly more negative numbers, right, as your amount. And so we never really want to let our amount become negative, so I like to turn that into a base case. So if my amount becomes negative, then I can return false, right? It's not going to be possible to create a negative amount using a sum because they tell us in the problem that our numbers are all going to be positive, right? You can never generate a negative quantity by summing up positive numbers. Awesome. So now I'll make sure we don't overshoot, right? We'll just return false here. That'll help us complete the brute force recursive here. So let's give that a shot. Always want to make sure that it gets a correct answer and it just times out, right? So now I know that this is a great candidate for applying memoization, right? We know that, like we said in the approach video, this currently has an exponential runtime, so it's far too slow. So to structure the optimized solution here, I like to split it up into my main method and my recursive method that also takes in a new argument, which, like we're used to from our last two problems, right, it should be a hash map. Cool. The keys of the hash map are just going to be the argument of my method, but it's only going to be the argument that changes, right? So if I look at the recursion here, I know that amount is really the argument that changes over time, right? The numbers argument, or the list of numbers, doesn't change, right? So I know that that list of numbers in my recursion doesn't really dictate the result, right? Because it never changes. I always return based on what the amount is. And so I'm just going to make the integer amount my key, right? The corresponding value is going to be just the return type of your method, so Boolean here. And I know that corresponds with, the return values on line like 20 and 24, and even in the base case. Awesome. I'm going to call this my memo once again. So let me go ahead and do some of the housekeeping here. So I want to get the hash map. And when I'm in my main method, I'm just going to invoke my overloaded helper method, give it the same amount, give it the same numbers, but you should give it a new hash map that's going to populate over time, so it's nice and fast. Awesome. At this point, what I want to do now is add my base case to check, hey, maybe an input amount I've seen before, right? So I'm going to add as a base case here. So if my memo contains a key that corresponds to the current amount I'm looking for, I just want to return its stored value because I would have stored the answer there. So return memo.get amount, right? Very reminiscent of your Fibonacci and Tribonacci. Awesome. Other things I need to do is I need to be sure to pass this memo by reference to all of my recursive calls. And I know that there are actually multiple recursive calls here because on line 25 I have a recursive call and it's in a loop, right? So you make a recursive call for every num of the list. So I'm going to over here pass in the memo. And now the only thing I'm missing is I need to find a way or find a location where I should add information into the memo, right? When do I put some keys and values into the memo? Like I said in the previous videos, I always locate my recursive return values, right? So that would be line 26 and line 30, right? And to be safe, you can memoize both of those return values, right? There's no point of memoizing your base case return values because those already occur in constant time, right? So there's no need to do it there. So over here, before I return true, you want to store in your memo for the key of amount, the same value you would have returned, right? So if you return true, then your stored value is true. Or if you return false, then in that case, your stored value is going to be false, right? And like we always say, the key that you kind of refer to through your entire memo logic is going to be the argument amount, right? So I'm not writing any keys that have to do with the sub amounts. To keep your code nice and clean, you write about your current amount you're passed in, right? You know that when you make your recursive call on the sub amount, that will become its own, like full amount, and then it will get cached anyway in the memo. So this should be good to go. Let's give this a test run, see how we optimize our solution. Great, and there we have it. Hey programmers, Alvin here. Right now let's go over the approach for this min change problem. So in this problem, what we want to do is take in two things as input. We're going to be given a target amount as well as an array containing some coin values. And what we want to do is return the minimum number of coins required to create the amount. So for example, since my target amount is 5, one way I can give back 5 cents would be to do 1 plus 1 plus 1 plus 1, or I can do 1 plus 2 plus 2, or I could even do 1 plus 1 plus 3, and also 2 plus 3. In this problem, what we want to do is choose the way that requires the least number of coins. So that would be the 2 plus 3. That would use only 2 total coins. And my function should just return that number of coins, which would be 2 as my final answer. All right, so let's start attacking this one by visualizing it. Let's sketch out what we would do for an amount of 4. That way we can actually finish it, because we're going to see that as we moderately increase the amount, the size of our problem actually grows pretty large. And so if you're doing all of these problems in order, and I always recommend that you do, you should recognize this one as a dynamic programming problem. So what I'm going to try to do is shrink my problem size, and then also notice any overlapping subproblems in the long run. And so I'm going to sketch things out as a tree. What I'll do in the nodes of my tree is write down my current amount that I need to generate. And I can break my current amount down into smaller subamounts. So let's say I start with 4 at my root. To generate an amount of 4, what I could do is use a 1-cent coin. And if I did that, my remaining quantity would be 3 as my amount. I could have also taken a 2, in which case I need to generate 2, or I could have taken a 3-cent coin, in which case my remaining amount would have been 1. So let's continue this pattern. Let's say I was at this 3 node. This node would have 3 more children, just branching for 1 cent, 2 cent, and 3 cent respectively. If I take a look at this 2 node over here, I can't actually use every option here. I should only branch twice. Because if I took the 3-cent coin, that would give me a remaining amount of -1, which I should probably avoid. Similarly, for this node of 1, I can only branch using the 1-cent coin. So let's say we continue this pattern for the entire tree, you would end up with this structure. And what we see visually is the decision tree that represents every choice of coin we can make until we hit 0. And so this is a tree structure that we've seen a few times in the course. What I'm going to argue is within the visual of this tree, you should actually be able to recognize what the answer is for this amount of 4. So take a moment, see if you can recognize any properties within this tree. Where can I find the answer to this problem? What we should do is interpret each path of this tree. So let's say I looked at this path. That would represent the sum of 1 plus 2 plus 1. In other words, I took a 1-cent coin and a 2-cent coin and then another 1-cent coin. And what I can say is that would represent the answer of 3, like a possible answer of 3, because I used 3 coins to generate my target amount of 4. That's only one possibility. We know in this problem we really want the minimal number of coins used. So that should translate into one of these shortest paths like this one. This would represent my sum of 3 plus 1, and that would have a length of 2. You can probably notice that there are a few other paths with a length of 2, but that's okay. We just want to return the smallest length possible, which would be 2. And so what we're really recognizing here is the minimum number of coins required to generate our amount would really be the shortest path from the root to any leaf within this tree, assuming a leaf terminates at a 0. So how can I do this more programmatically? Maybe we'll sketch this out as some recursion tree, right? So what I'll do is think of a return value for all of these 0 nodes. What we can say is our base case, if our amount is 0, then I should return 0. And so 0 is a great choice because it's a small number and I can't break it down any further. And I should also return 0 for that instance because the minimum number of coins required to make 0 cents would be to use 0 coins, right? Just use no coins. So above all of these base case nodes, I'm going to jot down my result of 0. And what I can do is start to evaluate these as return values. So let's say I was at this node of 1 over here. What I'll do is just receive 0 from my child call. What I should also do is add 1 to it. If I add 1, that would actually count the edge between myself and my child node. Because remember, when it comes to counting the number of coins, we're really counting the number of edges in a path through this visual tree. So let's say I was at this 2 node now. I was ready to evaluate it. What I do is receive both of these values of 1 and 0 for my children. And because I want the shortest path, or the minimum number of coins, my node needs to choose the smaller between the two. So I do 1 versus 0. I pick the smaller one of 0. But then what I need to do is actually increment that by 1 to count the edge between us. And what that would represent, this 1 designates the shortest way I can make 2 cents, which would represent this path highlighted in pink. Let's continue this pattern. So let's say I was at this 1 node, the 0 would just bubble up, then I add 1 to it because there's no decision to make. But now I can be at this 3 node. This 3 node is going to receive 3 options. It's going to choose the smallest among them, so just 0, but then it needs to add 1 to it. And at this point, I should be able to check for correctness. I have a green number of 1 above my 3 node, which means the minimum number of coins I need to make 3 cents would be just using 1 coin, which makes perfect logical sense because I have a 3 available in my coins array, so I could just take a single 3-cent coin. Let's continue this pattern elsewhere in the tree. At the root node of 4 in this tree, it's going to receive a bunch of 1s. Technically, it would choose the smallest among them, which would be a tie, given 1. And what I should do is always increment it by 1 to count the edge between myself and the children nodes. And this 2 represents the fact that I have a few different paths that could only take 2 coins, or 2 edges. It could represent this path, or even this path. So as we evaluated this tree, something really important we did was whenever we received multiple values from our children, so when we received multiple sub-solutions, what I do is choose the smallest among them, right? I know I need some min value logic present in this implementation because I want to choose the minimum number of coins possible. So I'll just keep that in mind when we implement the code. When we talk about the complexity of this, we've seen the structure before. Right now, we're going to describe the brute force complexity. If we say that C is the length of the coins array and A is the target amount, then the time complexity is going to be exponential, right? We know that the branching factor of this tree is going to be based on the number of coins, so C, right? Branching factor refers to, given a node, at most, how many times will it yield children? And I know my branching factor here is 3, and in the worst case, I have 3 branches coming out of a single node. My exponent here is going to be A because that would be the height of the tree. We'll say that the space complexity is going to be O of A due to the call stack, because if you look at the height of this tree, it would be in the worst case A. We say the worst case would be the scenario where I keep taking a bunch of 1-cent coins, giving me the deepest recursion possible. So if you start at the root node here and you just keep going left, you're going to see a sequence like 4, 3, 2, 1, 0, and that definitely is a linear pattern in A. So overall, we're looking at exponential runtime and a linear space complexity for this solution. The time complexity definitely needs some work though, right? We want to bring it down from an exponential. So like we usually do, we just want to memoize this one. We'll try to notice any duplicate subproblems. So looking at this tree, there are some duplicate subtrees I can notice. I can see these subtrees rooted in 2. So instead of recalculating that subsolution, I can save it and just reuse it. So I can trim out that piece of the tree. And I also have other subtrees rooted in 1. And I can also ignore those, right? The way I'll implement this is by using some constant time data structure like a hash map. I can store sub results as I compute them in that hash map and then reuse them later on. If that high level strategy seems confusing, don't worry, you'll want to wait until the walkthrough video where I actually show you the details on how to implement this in some code. So let's do a reanalysis of this. Now we're going to analyze this dynamic programming solution that uses memoization. The time complexity is just going to be A times C, so it's no longer exponential. It's really a sort of multilinear, right? Just multiplying my 2 terms together. We know that time complexity is going to be based on the number of recursive calls we make, and in this visual diagram, every node represents a recursive call. We still have a tree of height A, so that's where the A comes from. And what we're saying is, across every level of this tree, we have at most C nodes. So I think of A as the height and C as the width, and that would give me A times C nodes overall. And it's actually pretty easy to spot in this particular example. In the worst case scenario, at a particular level, we have only 3 nodes at most. That's because our coin array only has 3 options inside of it. The space complexity for a solution is just going to be O of A due to the call stack, and we'd be storing at most A different keys inside of our memo hash map. All right, I think I'm ready to code this one up. You'll want to join me in the walkthrough video now. At this point, we're done with the planning phase for our min change solution. What you want to do is head down to the links in the description below, where you can find the link to the min change problem, where you can code up the solution in Java with me. Hey programmers, Alvin from Structy here. What I want to do is go over the Java walkthrough for this min change problem. So you definitely want to make sure you watch the approach video first. This is going to be another dynamic programming problem similar to our previous sum possible problem. Like we said in the approach video, what we want to do here is optimize for the number of coins that we take into our sum. And so I'll implement that strategy exactly. What I want to do is start by laying out a base case. We know that in this problem, our base case should be about an input amount that is trivially small. And for me, that amount's going to be 0. So I'm going to check if the current amount that I'm looking for is equal to 0, then I want to return the answer for that amount of 0. I want to return an integer representing the number of coins I need to create that amount. So if someone asked you to generate 0 cents, what's the least number of coins you need to generate 0 cents? The answer there is 0 coins. So I'm just going to return 0. Then from there, I want to start writing my recursive scenarios. So I know that I need to take one of my choice of coins to reduce the amount. So I'm going to iterate over all the possibilities. So for me, that means I'll iterate for every int coin within the coins list. And what I'm going to do is I'm going to take the input amount and subtract this coin from it. That smaller quantity, that'll give me my sub amount, I'll call it. And from there, I want to recursively find the minimum number of coins needed to make that sub amount. So I can call my recursive method, pass in that sub amount, can pass in these same old coins. In the problem, they tell us that we can reuse a coin as many times as we need. Awesome. But now from here, I need to do some thinking. I know that this method call should give me back a number representing the minimum number of coins needed to make the sub amount. I'm going to save that number into a variable here just for readability. I'll call it sub coins. So that's the number of coins needed to make the sub amount. And I know I need to find the minimum sub coins for every choice of coin that I can take. So I need to perform some min value logic here. We know generally a min value logic means as we iterate over the possibilities, we maintain some outer variable here. I'll call it the min coins. And I have to think about a good default value for it here. Well, I know that in the context of the problem, they tell us that, all right, if it's not possible to make the amount with the coins, then you want to return -1. So I'll actually use that as an initial value here. So I'm going to set this up as -1. And I know that after the for loop at the end of my function, if I never find amount that works, I'm going to return min coins, which should still be the -1, right? But besides that, what if it is possible to make the sub amount? Well, if it's possible to make the sub amount, that means that subcoins would be a non-negative number, right? So I'm going to check if subcoins is not equal to -1. That means it was possible to make the sub amount. Since subcoins is a number of coins needed to make the sub amount, if I do subcoins +1, that should be the number of coins needed to make the full amount. And why do I know that? This additional +1 here is counting the single coin I took to get the sub amount. I'll save it to a variable called int num coins. So this is the number of coins needed to make the full amount over here. And now I could compare this against the min coins variable, right? So I'm going to check, hey, if this number of coins is less than the min coins, well, then I can replace the min coins with this new best number of coins, right? But it's pretty obvious here that when we initialize the min coins to -1, this -1 may persist over any valid number of coins here, right? Because -1 is already a negative quantity, right? So this -1 just acts like a placeholder, right, to represent an invalid quantity or the fact that we haven't found any valid number of coins yet. And so if the number of coins is less than min coins, or the min coin still contains that default value, then I can replace that default value with this number of coins, right? So I'm performing a min value logic over my minimum coins. So this code is looking pretty good. One thing we need to be aware of is when we calculate this difference here, when we do amount minus coin, that could give us a negative amount, right? Sub amount could be negative. So if we call min change with a negative number, we already overshot this base case here. So what I can do is just catch that with the base case. So if ever my input amount is less than 0, then what I want to do is return some value. I'll return -1 here. Because again, -1 in this problem represents the fact that the amount cannot be generated with the coins we're given, right? You cannot generate a negative amount when all of the coins that you're given are positive. So that's going to be a good extra base case there. So let's give this a test run. This should be our brute force solution for min change. If all is well, we'll add some memo into it and make it a little faster. So I'm getting an error here. Looks like I have a random typo current subcoins. That should just be subcoins +1, right? Let's give that a test once again. Nice, and this looks like our brute force solution. We know that an algorithm like this so far has an exponential runtime, just like we said in the approach video. So to speed this up, I'm going to use our memoization strategy. So like I always love to do, I'm going to separate it into a main function and then a recursive helper, right? So my main over here will just call my recursive helper. It's going to take in the amount as well as the coins, but also my memo, which will be a new hash map. I'll be sure to take that hash map as an argument here. So it's going to be a hash map. And I have to think about what the keys of this hash map are going to be. They should just be the argument that changes during the recursion, which is the amount. Notice that the amount is the only arg that changes. Coins stays the same, so I don't need to add it as a key into my map here. So I'll say my keys are going to be integer, and then the corresponding values are going to be just the return type of this method, which is also integer. I'll call that memo. Got to be sure to import hash map above. Looking pretty good. And be sure to pass along that memo through the entire recursion. Now I need to add an additional base case, right? I need to check, hey, if the memo already contains the amount, well then I've solved this subproblem before, just return the stored value in the memo. So I'll return memo.get the amount. Awesome. But if it's not, then I'll go ahead and actually perform the true logic and calculate recursively the answer. Right? And I know that now I need to actually add data into the memo where I return the result. So I look for the literal return line in my recursive case, and it's only one return statement here in the recursive case. That's line 35. So literally what I should do is I ought to save this into my memo. So I can do memo.put. And I'm going to use the input amount as my key. Always use the original argument. Make the corresponding value min coins. And you still need to complete the return value. So like before, still logically return min coins. You're just making sure you store it in the memo before you leave this recursive call. Nice. So with that logic built around my brute force, by adding the memo, we should get a better runtime here. Awesome. And there we have it. Here we start to really see the power of this strategy of first solving a brute force recursion and then applying our memoization trick right around it. Really, the hardest part of a situation like this is to solve the brute force recursion in the first place, right? But that lets you focus on just the correct logic. And then afterwards, you speed up that logic using this additional data structure. All right, programmers, that's all I got for this one. What I want you to do is practice this, and I'll see you in the next one. Hey programmers, I just want to take a little break from our dynamic programming material to tell you about Structy. Structy is a complete data structures and algorithm course that you can use to prepare for all of your technical interviews. It's actually the course you've been seeing me use throughout the video tutorials. I'm going to be your teacher through the entire Structy curriculum, and in the Structy course we cover all of those essential interview topics like graphs, trees, dynamic programming, and more. And like you expect for every single problem like you've seen in this dynamic programming course, we're going to support it with animations as well as code walkthroughs, and you'll be able to code up all of these solutions on the platform and test your code in Java, C++, JavaScript, and Python. So if you're enjoying this dynamic programming material, I recommend you head over to Structy where you can practice things further, whether it's dynamic programming or those other essential topics. And of course, you're going to be joining me for all of those video walkthroughs, so I'll see you there. Without any further ado, let's hop back into our course. Hey programmers, Alvin here. Right now let's go over the approach for this count paths problem. So in this problem we're going to be given a grid. What we want to do is travel from the top left corner down to the bottom right corner. And here we want to return the number of ways that's possible to traverse through this grid. And the caveat is we can only move to the right or downward. That means we can't go up and we can't go to the left. And so for this particular grid, let's talk about the different ways we can travel through it. One way would be to go right, right, down. Another way would be to go right, down, right. And finally, the last way would be to go down, right, right. And since there are 3 possible ways to travel through this grid, we should just return the number of 3. So this should be a counting problem for us. However, this problem is a little more nuanced. They say that some positions are going to be occupied by walls, and we can't travel through them. So if I had a wall like this in the top right corner, then one way to travel through the grid would be right, down, right, and the only other way would be down, right, right. So let's trace through the strategy for this one by looking at a larger example. If I was given this 3x3 grid, I'll also put a wall in the top right corner. Let's start by labeling the indices for our rows and columns. We know that we start in the top left corner, so that would mean row 0, column 0. And what I want to start to do is try to give myself a way where I can denote every option I have, right? How can I mark the decisions I can make by traveling through this grid? So I'm going to visualize this one as a tree. So if I start at position 0, 0, I can make that the root of my tree. If I'm at this position, I'll think about my options that I have. I can either move downward. If I move downward, that would increase my row by 1, but keep my column the same, giving me 1, 0. Or if I went to the right, I keep my row the same at 0, and I increase my column by 1. And that would be the only 2 options I have from this root position. And I can just apply this logic recursively. So let's say I was situated at the 0, 1 node right now. So I'm over here. I know that my options are more limited now. I can't move to the right because I have a wall in my way. So I'm going to need to make sure I code that one up. And I can only move downward here. And that would mean increasing my row by 1 and keeping the column the same. And so let's carry over this pattern to draw out the rest of this tree. We know that given a node, at most it's going to have 2 children, representing my downward or rightward movement, and that would mean either incrementing the row by exactly 1 or incrementing the column by 1. However, we should not do that move if we go out of bounds or run into a wall. So the full tree would look something like this. What's great about this tree is if I start at the root and travel to a leaf node, that would represent one of the paths I can take through my grid. In other words, if I look at this path in my grid, I can represent that using this path in my tree, which is a really nice way to interpret this problem. And so let's start to realize how we can encode the base case in this problem. What you should be realizing is we're visualizing this as a tree, which usually gives us a nice way to implement this as recursion, right? So if I look at all the leaf nodes here, I always terminate at 2, 2, because that would represent the bottom right corner of my grid, which is the goal. And so if I'm at the bottom right position of 2, 2, what should I do here? Well, I have to think about the return value for my function here, right? They say they want a count. And so what I should do is treat this 2, 2 position as if it's its own input. So if someone asks me in how many ways can you get from the bottom right position to the bottom right position, the answer would be 1, right? There's only one way to do that, and that would be to just stay there, right? Because you're already at your goal point. And so I'm going to make all of these leaf nodes or all these base cases return 1. And having these calls return 1 seems useful because I know I need to tally up a count in this problem. So how would we start reconstructing our larger solutions here? Well, I would just really bubble up these ones, right? So let's slow down at this 1, 1 node over here. We know that this node has a little more work to do because it's going to receive 2 values. And so what I should do is bubble up both of these values, right? And then this node should just add them together. So 1 plus 1 gives me 2. And so what are we saying here? If I pause, I should have some logical information in the subtree. What it should be saying is that there are 2 ways to get from the position 1, 1 to the bottom right corner. I have this path, or I have this path. There are 2 different ways to get from 1, 1 down to your bottom right corner. So I'll just carry over this pattern, keep reconstructing all of my solutions. And as we get toward the top of our tree, we are going to get the final count of all of the ways to travel from the top left to the bottom right, giving us our final answer of 5. What's great about visualizing this one as a tree is it really describes the decisions we can make as we travel through the grid, right? We know that this gives us a binary tree because for the most part, when we're on the inside of the grid, we only have 2 options, right? You can either move downward or to the right. And that'll help us decide the complexity of this brute force algorithm. So if we implement this algorithm as it is, just with some baseline recursion, we say that R is a number of rows and C is a number of columns. This will give us an exponential runtime, meaning there are an exponential number of nodes in this tree. Really, it's 2 to the R plus C power. So the base of 2 comes from the fact that this is a binary tree, and in the context of our problem, that means I can only move downward or to the right, so you only have 2 options. And I'm saying that the height of this tree is R plus C, right? Because you know you want to start in the top left corner, 0, 0, and travel to the bottom right corner, what you have to do is actually traverse a path that is exactly R plus C moves long, right? Because you need to move through all of your rows and all of your columns. For the same reason, I can say that the space complexity is going to be R plus C just due to the stack depth, right? Stack depth is equal to the height of this tree, which we just said is roughly R plus C. And so overall, we shouldn't be too satisfied with the time complexity of this one, right? Typically, something exponential would be too slow for our liking. And so what we should do is recognize that we actually have this visualized as a nice dynamic programming problem. What you should do is take a moment, look at our visual tree, and notice if you can spot any duplicate subproblems, right? Are there any overlapping subproblems here that I can memoize? So we actually have a duplicate subtree over here rooted in 1, 1. What I could do is just save the first time I calculate it. That way I don't have to fully recurse down my tree the second time around, effectively memoizing my duplicate function calls, which in the context of my tree visual just means that I prune out some branches. There are some other subtrees here. I can look at this 2, 1 subtree. I can also memoize that away. And we know as we grow the problem size, in other words, if someone gave me a larger and larger grid, I would have more and more overlapping subproblems, so I'd benefit more and more from memoization. Like usual for us, the way we'll implement this is by using some hash map data structure. I'll save that detail for the code walkthrough though. So what do we know about the new and improved complexity of this one, right? We're going to implement our dynamic programming using our classic memoization strategy. So like usual, R is a number of rows and C is a number of columns. Now it would be the case that our time complexity is R times C, right? It's still the case that our time complexity is driven by the number of recursive calls we make. And now we would be making roughly R times C different recursive calls, right? And how do I know that? Well, in the context of what I'm going to memoize into my hash map, I'm going to put positions, right? Notice that each node in this visual is a position of row and column. And I know that there are exactly R times C different rows and columns. So once I store a row and column into my memo, I would never have to fully recompute it, which gives me my time complexity of R times C. Likewise, now is the case that my space complexity is R times C, taken mostly from the size of that memo, right? Every position is going to be a key, and so I have R times C different keys in my memo object. All right, programmers, I'm sure you're itching to see how we actually implement this one in some code. So right now you'll want to join me in the walkthrough videos. I'll see you there. Now that we're done sketching out the solution behind this count pass problem, what you want to do is head down to the links in the description below where you can actually access the prompt and the test cases for this count pass problem. And we'll code up the solution in Java together. Hey programmers, Alvin from Structy here. What I want to do is go over the count pass problem in Java. So like we said in the approach video, we're going to frame this problem like a dynamic programming one. This is going to be a little different compared to our very classic like graph, grid problems, because in this problem we can only move rightward or downward. That means that we can't get caught in any cycles, right? So I don't have to do any visited logic or anything like that. However, what I will do is solve this one with a brute force recursion and then apply our memoization strategy on top of it to get a really fast dynamic programming optimized solution. So to get the ball rolling on this one, I know I need to start tracking like a current position as I traverse through the grid. So I'm going to split this one up into my main method as well as my helper. And my helper is going to take in my current row and current column information. And then in my main method, I'll just pass control to my helper, and I'll give it the starting point, which is a top left corner, which means row 0, column 0, pass along the entire grid to reference. Then from here, I'm going to structure this one as like a depth first recursive solution, more or less. And so I'm going to start with the base case. So what's my goal here? Well, my goal is to find the bottom right corner of my grid so I can stop traversing if my row and column is the bottom right. So be careful of the math here, right? To be in the bottom-most row, that would mean that the row is equal to grid.size minus 1. That means the bottom row. Similarly, you want to check if the column is equal to the rightmost column. So that would mean grid.get0.size minus 1. Right? So this is checking if I'm in the bottom right position. Then what do I want to do? Well, I want to return overall the number of ways to reach the bottom right corner from this current position. Well, if you're already in the target position, then you don't need to do anything. So that's one way that you can get to the bottom right corner. You just do nothing, right? Because you're already there. So I'll return 1 in this instance. But I have to think about some other scenarios, right? It could be the case that maybe my row and column is out of bounds. So I want to avoid that. And so I'll check maybe a very similar condition here. I'm going to check if I'm out of bounds, that would mean that my row is equal to grid size, or my column is equal to grid.get0.size, right? Notice that I'm turning this into an or, right? Because if your row is too large or your column is too large, well, if either of those are true or both of those are true, then it's an invalid position, so you're out of bounds, right? And if that's the case, I still need to give a logical return value, right? I always want to have consistent return types. So even in this base case, if I'm out of bounds, I want to return an integer. And that integer needs to represent how many ways from this position I can travel to the bottom right corner. Well, if you're out of bounds, there's no possible way to ever get to the bottom right corner at that point. So you want to return 0, right? There are 0 ways to travel from an out of bounds position to the bottom right corner. So I have my base cases looking pretty good, but there's one more to capture here. They also tell us that, all right, some positions of your grid are not open. O stands for an open position. If a grid position contains an X, that's a wall that I cannot travel through. So I'm going to actually add that into the mix here, right? It might be the case that if my grid.getR.getC, so if my current position is equal to an X, well, then I can't traverse through it. right? That's also a dead end, kind of like out of bounds. So I'm similarly going to return 0. Awesome. Do note the important order of these two cases over here, right? I'm making sure that I only try to access like the innermost element of my 2D grid after I check that the row and column are valid, right? And I know that I'm using some valid RNC to get a position of my grid. It's just that that position contains an X. So these are all of my base cases here. Now I can start structuring my recursive case. And I know that from any position that I'm at, I have, two options to take. And those two options will turn into my two recursive calls, right? So I'm going to call count paths. You could move downward. So you could move down a row, keep the column the same. But you can also move to the right. So you can do count paths of the same row, but increase the column. Nice. Now to think about what these two recursive calls return. They return a number, right? This one on the left returns to me the number of ways I can get to the bottom right corner or get to the goal if I move downward. This tells me the number of ways I can get to the goal if right now I move to the right. If I take the sum of them, that gives me the total ways I can get to the goal from this position. Because from this position, you can only either move down or move to the right. So this is looking like some core logic. This looks like the shape of my brute force. Not much logic to it overall, just some tricky edge cases here for my base case. And so let me give this a test run. I'm looking for some correct output, so I'm passing some test cases, but probably timing out for large inputs. And there we see it. So like I always love to do, now I need to apply my memoization to it. So I'm going to set that up. You always want to use some fast lookup data structure to store your memo, right? And so for us, use something like a hash map. And I'll pass along that hash map inline over here. So new hash map. And I'll take it as an argument. And here where I design the hash map, I have to be a little more particular, right? So generally, for the keys of my hash map, I always use the changing arguments into my recursive method here, right? So if I look at the arguments that change during my recursion, it's the row and the column. Right? The grid itself is always the same throughout the full recursion, so I don't need to encode it into the keys of my hash map. And so I really need to represent a row and column pair or like position as keys of my hash map, because depending on the row and column, you get a different answer. And so to actually store that key, I'm going to use just a list of only two things of a row and column. So it'll be a list of integer, and I'll just guarantee that I make sure that those sublists are always going to be of length 2, right? Just pairs of row and column. And corresponding value is going to be the return type for my method, which is just integer as well. Nice. Call this memo. And now let's add our memo checking logic. So past these base cases, what I like to do is form the key I'm going to use into my memo. So I'll create that key here. It's going to be a list of integer, really just a pair. I'll call it my position. And it's going to be just a list of the row and column. Nice. And I can check, hey, if this position is in the memo, so if memo.contains key position, then I can return the associated value with it. Because that means I've seen this recursive call before, so I can just instantly find the old result. So return memo.get position. Again, the key trick here is I'm using this position because it contains the row and column arguments, right? So I'm using that entire entity as a key into my memo. Nice. Then from there, like we're used to, I should be sure to pass the memo to my calls here. And whenever you see your recursive return value, which is line 30 for me, you want to store that result in your memo before you leave, right? So I'm just going to store this into an int result. Be sure to put that in your memo. So memo.put. This is put a key of position with the result, and then just return the result. Nice. So with those changes, pretty classic changes to the previous problems that we've been doing, except we're having a little more complex of a memo key here. Let's give that a shot. Awesome. And there's our solution for count paths. Hey programmers, Alvin here. Right now let's go over the approach for this max path sum problem. So in this problem, we're going to be given a grid, and we start in the top left corner, and we want to make our way to the bottom right corner. This grid's going to be populated with some numbers, though. What we want to do here is return the path containing the maximal path sum. In other words, there are a few ways we can travel through this grid. One way would be to use this path, in which case your sum would be 14. Another way would be to use this path, in which case your sum would be 12. And finally, you can use this path, in which case your sum would be 18. And between these three options, I should choose the 18, right? And so that would be the max path sum for this grid. So let's cut to the chase and describe the strategy for this one, and we'll step through exactly this example. So we'll label the row and columns, and we also know that we start, of course, in the top left corner. This is really just a spin-off of our last problem, so hopefully you visualize this one as a tree, right? A binary tree, because we only have two options at any point in time, right? You can either move downward or to the right, and sometimes in just one of those directions, depending on whether or not you're at the border of our grid, right? So we'll start at 0, 0. From this position, I have two options. If I went downward, I would increase my row by 1. Notice that each pair within a node here is a row and column. Or I could have moved to the right, in which case I would be at 0, 1. That would represent my two moves. Let's say I was situated at this 1, 0 node. Here I only have one move possible to make. I must move to 1, 1, right? That represents a move to the right. If you look at my row and column indices, that's because I can't go downward anymore because I'm already in the last row. If I take a look at this position over here, I do have two options, right? I can go downward or to the right, giving me 1, 1 and 0, 2 respectively. And we can build out the full tree from this point. We know that we must terminate at position 1, 2, because that would be the bottom right corner. So I know that that is our ending point, right? So that's going to be my base case. I know in this problem, I want to choose the maximal path sum, so I want a max sum, but how can I start accumulating a sum in the first place? And so what you have to do is ask yourself, if I'm already at the end position, what is its max path sum to the end position? And that would just be the value of 2, right? That's exactly the number in that ending position. So for my base cases, I'm just going to return whatever number is in that final position. Then from here, I know that these values are going to return. So let's say we were situated at this 1, 1 node. It's going to receive a value from its child call because we know we're visualizing this in a recursive way. And what I should do here is note what position I'm at. So 1, 1 would be this position containing a 6. I want to accumulate a sum here, so I should do 2 plus 6, giving me 8. So this node's going to return 8 to its parent. So this 8's going to bubble up a little bit more. And if I think about this 1, 0 node, that represents my current value of 5 over in yellow. And I would do my 8 plus 5, giving me 13. So that would be a partial path so far. So we'll continue this process on our right-hand side. We know that these would just bubble up, and we would add the respective values at those positions. Things get more interesting when we're at this 0, 1 node, though. So for this node, it's going to receive both 8 and 14, right? It's just going to return back up like we always do. And I have to make a decision here. Since I want the max path sum, this node should choose the larger of those two values. So 14 is bigger than 8, so I prefer the 14 here. But I should also still add the value stored at my current position. So if I look at position 0, 1 within my grid, that would be this value of 3. So I add 3 to the 14, giving me 17. And finally, this takes place again at the root. So if I'm at 0, 0, I'm going to receive the 13 and the 17 for my children. I choose the bigger value of 17, and then I add my position itself, which has a value of 1 inside. And that gives me a final answer of 18. So the way we reconstructed our sub-solutions into higher level solutions was to choose the larger of our two children and then add ourselves to it. That way I get some max value logic while also summing our path. We talk about the brute force complexity of this algorithm. If we say that R is the number of rows and C is the number of columns, then our time complexity is going to be exponential, just like we saw in the last problem. The base of 2 comes from the fact that given any position, we have two options, right? We can either go down or to the right, and I make R plus C the exponent because that would be the height of this tree, right? That would be the length of any particular path. I know any path that travels from the top left to the bottom right must cover all of the rows, R, and all of the columns, C. And so the entire path length would be R plus C. In a similar way, I'll say the space complexity is R plus C due to the stack space required by this recursion, right? If the height of this tree is R plus C, that means the stack space used by my recursion is also going to be R plus C. But a keen observer would note that I can do better because this is a dynamic programming problem. So what I'll do is take a moment, look at this tree, see if you can find any overlapping subproblems. And although this example was small, I can already see some overlap. If I look at this node rooted in 1, 1, I see it here, and I also see it here. And we know the punchline is I should only have to calculate these nodes exactly once. So I should be able to trim out a little bit of the tree by using some memoization. And as we actually increase the size of our input, as I get a larger and larger grid, I would have more and more overlap that I'm able to kind of forego using some memoization. Like usual, we're going to implement this using a hash map, but I'll save those finer implementation details in the walkthrough video. If we implement memoization properly for this one, we're going to bring our complexity down to linear, right? So we're going to have a time complexity of r times c. And that's because there are r times c different nodes to actually cover now, right? I know I'm going to put the positions as the keys of my memo, and there are r times c unique positions. In a similar way, it's now the case that my space complexity is taken over by the size of my memo, which is also r times c because of the number of keys, right? I have r times c keys because I have r times c positions. All right, I think I'm ready to code this one up. You'll want to join me in the walkthrough videos now. Hey programmers, welcome back. What I want to do right now is go over the Java walkthrough for this max path sum problem. So this is going to be a small variation of the previous, grid dynamic programming problem, except this time we want to find the maximum as we travel from the top left of our grid to the bottom right. So I'm going to start by setting up the same initial structure. So you'll want to track a position as you kind of traverse through your grid. And so I'm going to add additional arguments to this method. So I'm going to need to track my current row as well as my current column. Nice. And then from there, what I want to do is start laying down my base cases, right? So for my base cases, like you expect, there are a few. I need to check if I'm out of bounds. So if my row is equal to grid.size, that means I'm just outside of the grid. Or maybe my column is equal to grid.size, or rather grid.getZero size, or I'm out of the column range, right? In either case, you want to return some integer, right? How can you represent an invalid integer, meaning it's not possible to travel to the bottom right corner using this particular position? Well, because I want to perform overall like a max path logic or max value logic, I know my logic is going to be preferring any larger integers. And so whenever I encounter like an out of bounds or invalid position, I need to return some very small number, right? And so for me, I think the best way to solve this one is going to be to use like a negative infinity concept. And so in Java, really your only choice for like a true negative infinity is going to be in the double type. So I'm going to say double dot negative infinity, which means I have to adjust some of my types here, right? So I guess I'm going to make this return a double. That's totally fine. I'll just be sure to cast it back in my main method here. All right, so what am I saying? Well, just so I can have access to like negative infinity in my recursive over here, in my main method, it's going to call maxPathSum with the initial row, initial column, as well as the grid. And I know that this is now defined to return a double. You're going to get an error in Java if you try to return a double from an integer return method. So I'm just going to cast it into an integer by just doing that. Really straightforward. So I'm only going to convert at the very end, which is fine. All right, so beyond that, I need to just handle the case where I actually hit my target in a base case. So that'll be a similar condition, right? You want to check in English if you're in the bottom right position. So if your row is the last row and your column is the last column. And so you want to return some number here. And overall, you want to be adding up the values in your grid as you travel along them. So in your base case, you want to return an actual value. You want to return the value of your current position. So you want to return grid.get r.getC. So what am I really saying here? So let's say that we're performing our recursion and we hit this base case, meaning we're at the bottom right corner. So that means I'm at this position. What I'm going to do here is return the value at this position. So I'm returning the value of 1. I'm going to return it because I need to eventually add up all the values along my winning path. And the end goal is still part of my winning path here. Nice. And so now that I have these base cases in line, what I want to do is start forming my recursive case. So I know I'm going to have two recursive calls, right? Because at any position, I have two options. I can either go down or go to the right. So I'm going to call max path sum. Going downward would be r plus 1 c grid. And going to the right would be max path sum of the same row, increase the column, same old grid. Nice. And here, what I want to do is prefer the larger sub answer, right? Because when I take a path through my grid, you either go right or you go down, right? And I know that these recursive calls give me back a number. They represent the sum of the path if I travel through the right or if I travel downward. And I want to choose whichever sub-result is bigger, right? Because right might give you a bigger sum or going down might be a bigger sum, but you can only take one of them. And so to choose just the maximal between these two numbers that I get back, I'm just going to use the built-in math.max. You can also write some conditional logic. This is probably the easiest way to write this though. So just choose the bigger value between these two methods. But I should also be sure to add my current position into that answer, right? So I'm going to do grid.getR.getC and add it into the bigger between my going down choice or my going rightward choice, right? This gives me the logic of summing up all of the values along a particular path. Awesome. So let's give this code a run. This should be our brute force solution, it looks like. Nice. And if all is well, we should start timing out. And there we have it. So let's improve the runtime of this one by adding in our memo. So that's going to be a hash map. This is going to have us use a hash map where the keys are going to be positions, right? Because the row and column is what determines the answer here, because those are the arguments that change. So I should pass along a new hash map here. And over here, I'll define the type. So hash map, the keys are going to be positions. So just kind of list pairs of two integers. Corresponding value is going to be, looks like double. I'll call that memo. So like we always do, we want to add our memo checking logic as an additional base case. So I'll start by forming the key first, which is really just a position pair, list of the row and column, and then start by checking if it's in the memo. So if memo contains the key of position, then return its corresponding stored value. So I'll return memo.get position. Nice. And then beyond that, I need to be sure to pass along this memo so it's shared through the entire recursion. So just pass it by reference here, not a big deal. And like I always say, right, the key is to now just find your recursive return value, which is this thing over here. You want to store it in your memo before you return, right? So this long expression just is a double. It's like just a sum, right? So I'll save that as a result. And this is going to be a double. How do I know it's double? Well, it's obviously double because of this over here. What I want to do is store it in my memo. So memo.put, use your original arguments, your original key here, make the corresponding value the result. And then like before, still return the same old result. The only additional step you took was to store it for a rainy day. Because I know later on, if I ever encounter this position again, I would hit this conditional and I can return that sub-result in constant time, which gives me a much better performance here. Let's give that a test run. Added our dynamic programming strategy. And there we have our very snappy code. Hey programmers, Alvin here. Right now let's go over the approach for this non-adjacent sum problem. So in this problem, you're going to do is take in an array containing some numbers. What you want to do is return the maximal sum of non-adjacent elements in this array. So that means we can never take two numbers that are next to each other within the array. For this particular input, the answer should be 16, because the max non-adjacent sum would contain the 4 plus 12. Here we should notice that we can't take a sum like 12 plus 7 because those two elements are adjacent within the array. Let's take a look at another example. Let's say I was given 7, 5, 5, and 12. In this particular scenario, the output should be 19, representing the sum of 7 and 12, which is totally fine because they are non-adjacent in the array. So let's come up with a strategy for this one. We'll step through the example of 2, 4, 5, 12, and 7. What I want to do is figure out a way I can come up with all the possibilities for numbers I take into my sum and numbers I exclude from my sum. Because we know that based on the numbers we take, that would actually limit our options later on. So let's say we started to encode this as a recursion tree, right? So I'm going to describe all of the decisions that we could take as we come up with a sum for this problem. So I'm going to start with my original array at the root. What I have to do is come up with a decision right now. Let's say I was making a decision for the first element of this array. So if I took 2 into my sum, then I know my resulting elements I can choose from is really just 5, 12, and 7. So notice how I did this left branch over here, right? I'm writing 2 along the edge to represent that I'm taking 2 into the sum. And notice how I make my array smaller in that left child. I just have 5, 12, and 7 because I cannot include 4 in that next call, right? Because including 4 would actually mean that we're giving ourselves the opportunity to take an adjacent sum, right? If you take 2 right now, then you can never ever take 4. So that's why I exclude it. However, at the root, we could have also just not taken 2 altogether. In which case, when you look at your next subarray, that would just be 4, 5, 12, and 7, right? If I don't take the 2, that means I'm excluding it along the edge on the right-hand side, then I can totally give myself the opportunity to take 4 in the future. So I'm going to include it in the next array. So let's carry this pattern further. Let's say we looked at this left node over here. What I have to do is always make a decision about the first element of this array. So for the 5 node, if I decide to take it, what I can do is then look at the remaining elements of just 7. Right? I don't pass 12 into the remaining subarray because if I take 5, I cannot take 12. However, I could have also just not taken 5 altogether, in which case my remaining elements are just 12 and 7. So by now it should be clear how we generalize the steps here, right? Given any particular array, what I can do is either take the first element or not take the first element, and that would decide what remaining elements I can choose from, either slicing off 1 or 2 elements from the front of my array. Let's say we evaluated this node over here. If I take 4, then that would give me a remainder of 12 and 7. If I don't take 4, then my remainder is 5, 12, and 7. Something interesting happens at the 7 node, right? So in one scenario, I can take the 7, in which case I really just have an empty array left over, right? There's nothing else to choose for because that's my last element. And in the scenario that I don't take 7, you would still have an empty array left over. So notice how the 7 node terminates in really 2 empty arrays. Finally, we'll evaluate this 12, 7 node. If I took the 12, then I would have an empty array because if I take the 12, you cannot take the 7 anymore. And if I don't take the 12, well then I can totally take the 7 for my next decision. And at this point, we would actually have a larger tree, right? There are still some nodes I need to evaluate here fully, but what's great about this is I can actually notice that those are all duplicate nodes. In other words, I've noticed that this is a dynamic programming problem. Right? If something has dynamic programming present in it, then I should be able to recognize any overlapping subproblems. In the context of this tree, I just have to notice any duplicate nodes, any duplicate subtrees. I can notice a duplicate subtree rooted in 7, right? So I don't need to re-explore this 7 node again. Likewise, I can notice a duplicate subtree rooted in 12, 7. And there's even more than that. I even have a very large subtree rooted in 5, 12, and 7. And so I'm going to save a lot of complexity by saving some of these subsolutions as I compute them. So let's talk about how we can recompute our final answer from the problem now that we broke it down. What we should notice is toward the bottom of our tree, we're going to have leaves that represent empty arrays, which does feel good because we know as our problem size gets smaller and smaller, that would mean a smaller and smaller array, right? Less and less numbers to choose from. Let's make our base case about the empty array. In other words, if someone gave me an empty array, then the max non-adjacent sum would be 0, right? Just take no elements of the array because you don't really have an option here. So for all of these empty nodes or the empty arrays, I'm going to have them return 0. And I know I'm going to make that a base case. Let's say we wanted to evaluate now at the 7 node, how will it use those sub-solutions? Well, if I take a look at the left return value, that's going to bubble up. But what I should also do is add the 7 along the edge, right? The yellow 7. That represents the fact that I was taking and including 7 into that sum. So I have a 7 on my left. And for the right-hand child, that just bubbles up as it is, right? Because I did not include 7 for that particular subproblem. And at this point, I have this node choosing between 7 and 0. Since I want the max non-adjacent sum, I choose the larger between the two. So I should return 7 in this instance. So now let's evaluate this 12, 7 node. Since I just evaluated the 7 node into its result, I'm just going to jot down that answer here. And I know I would implement that probably using some memoization. But as I carry on my return values here, the left-hand 0 is going to bubble up, but I add the value along the edge because I was including 12 to that sum. So I have 12 on my left and 7 on my right. I choose the larger between the two, and I should return 12, which makes sense because if you think about it, given just the small subarray of 12, 7, the max non-adjacent sum would be 12, right? Just choose 12. Definitely don't choose 7 because that'd be smaller. Now that I've evaluated this 12, 7 node, I know I can save this result for later on. So I'm going to jot it down on that duplicate node over here. Now let's evaluate a little higher up. We'll carry over the same logic as before, so I return these values and I add the 5 along the left-hand edge, giving me 12. At this point, I choose the larger between 12 and 12. It's really a tie here, so I'll just return 12. So I've just computed the sub-solution for the array 5, 12, 7, and I actually have a duplicate node on the right-hand side, so I'm going to jot that down. If I evaluate this node now, things bubble up. Along the left-hand edge, I add a 4, giving me 16. So I do 16 versus 12. I choose the larger one, which would of course be 16. Finally, at the ultimate root, I return these two values, but the left-hand edge gets a +2. And I choose the larger between 14 and 16, giving me my final answer of 16, which would be the correct answer. Let's talk about the complexity for this one. So if we say that n is the length of the numbers, what we could do is analyze the brute force complexity of this, right? So if you did not optimize this by trimming out some duplicate nodes in your subtree, you would have an exponential runtime. In other words, your time complexity is 2 to the n, and your space complexity is just O of n. We can say that the time complexity is 2 to the n here because for every node of this tree, it's going to give at most 2 children, right? So in the worst case, from one level of the tree to the next, I double the number of nodes. And I also know that the height of this tree is going to be n, right? The height of the tree is going to be n because in some scenarios, I could just keep removing the first element of my array again and again. And that means that the deepest recursion would require n stack frames on the call stack. But like we said, we can optimize this with some dynamic programming, with some memoization. If you did things correctly here, you would get a runtime of just O of n, so linear, and a space complexity of also O of n. One thing to note for this one is if you really want to get the linear runtime out of this problem, you're going to have to figure out a clever way to actually represent a logical shrinkage of your array. In other words, if you look at the nodes of my tree, I'm representing the array, and I'm chopping off some elements of the array at any point in time. What you don't want to do is create many copies of the array, because I know creating a copy of an array would itself run in a linear time. If you're creating a copy within every recursive call, it's going to be pretty inefficient. I will actually save that detail for the implementation video. And so if you're wondering how to exactly implement that pattern, you'll want to join me in the walkthrough video. I think let's hop to it. Hey programmers, Alvin here. What I want to do right now is go over the Java solution for this non-adjacent sum problem. So like we said in the approach video, to solve this one, we're going to solve it using some recursive brute force algorithm, and then apply some memoization on top of it. And so to get the ball rolling here, I'm going to need a way to give myself the ability to look at different pieces of my input list here. I know at any point in time, I want to shrink my input list smaller and smaller toward my base case. And so to set up that structure, I think it's good to have access to like a starting index. So I'm going to overload the method name here. I'm going to give it another argument. I'll say int I. And this will represent the starting index of the sublist that I'm considering. For example, if I is the number 2, that means I should be analyzing the list starting at index 2. So index 2 all the way through the end. That means top level over here, when I call my helper method, I'll call non-adjacent sum, given the same nums list, and then initialize I to be 0, because you want to start considering the full list, starting at index 0, going through the end. This will help us avoid any slicing or creating copies of the list as we go, giving us a faster solution. And so to get the ball rolling on our brute force, let's consider some base cases here. And so I know I want to check a base case if my list that I'm considering is empty, right? So I'm going to check. For me, a logical empty linked list would mean that my index I is at the end or past the end of the list here. So I'll check if I is greater than or equal to nums.size. Notice that here I'm technically checking if I is out of bounds of the nums list, because I know the last valid index of a list would be size -1. So if that's the case, what I want to do is return 0. For one, I'm trying to be consistent with the return type of this method, which should be of type integer, and 0 is definitely an integer. And I'm returning 0 because it represents an empty sum. Because I know overall in the context of this problem, I want to maximize the sum that I take. And so with that, let me also start forming my recursive calls. And these recursive calls should really mimic the logic that we expressed when we drew the approach video tree, right? And so we have really two options here. I'll kind of lay them out. Well, what you could do is take the number at the front of your list. So for me, the front of my logical list would be the item at index I. So if you took that number, you could say nums.get I, and you want to recursively add it to the sum of the remaining part of the list that you can take from. If you take the element at position I, then when you call non-adjacent sum, you'll give them the same nums list, but you want to manipulate I. Obviously, I want to increase I, giving myself like a smaller logical list. What you want to do is pass in I plus 2 here. And so it's pretty clear why we're not just passing in the same old I. Well, for one, we already took the element at index I into our sum, and we're adding it to our recursive sum here. We shouldn't pass in I plus 1 because that would be a number adjacent to I, right? And if we take I right now, we know we can't take I plus 1 later on, because the whole point of this problem is you can't take two elements that are adjacent in the list. And so the earliest number we could take from there would be I plus 2. Right, and this is very indicative of the logic we expressed when we drew the tree. So that's only half of the pattern here. There could also be a scenario where I don't take my current element at index I, and instead I just do non-adjacent sum of nums, and then I pass in I plus 1 here, right? So now I do have the option of taking the element that's right after I. Nice. And I know that these two variables over here, or these two expressions, they give me back a number, right? They represent a sum. What I want to do is now work in my max value logic. I want to choose the maximum answer between these two choices, right? The choices you make are either you take your element at index I or you don't take your element at index I. So I'm going to choose the maximum between them. For me, I could just use the built-in math.max. It just takes in two arguments and returns the bigger value between them. And now that I'm choosing the maximum between these two quantities, you just want to return whatever that maximum is. So this code's looking pretty good. Let's give this a test run so far. Really short logic, but we do want to optimize this in a moment. So we're passing our initial test cases and we're timing out on test case 04. So we're in good shape here. We know that a problem like this does have an exponential runtime, so it's too slow to run. But I can add some memoization logic into the mix here to improve that. So like we're always used to, should know this formula by now. I'm going to bring in the hash map, and I'm going to pass it into my recursive method here. When it comes to the structure of this hash map, its keys are always going to be like the changing arguments to my recursive method. So I'll pass in a hash map here. For me, the keys need to represent my integers I, right? So I'll make the key type integer. Corresponding value is going to be the return type of the method, which is also integer. So this hash map maps integers to integers. And let me add my base case to check if a key already exists in the memo. And for me, the key is really the argument I, right? So if the memo contains the key of I, then just return the stored value, because I would have stored this subsolution previously. So return memo.get I. Now on the flip side, I have to locate my recursive return value, which is this expression over here, and I want to store it in the memo before I leave, right? So I'll just save this into a variable. I'll call it result. And I'm still going to complete the return value. That way we don't change any of the actual arithmetic in this evaluation, but I do want to save this result. So before I leave, I'm going to do memo.put, use your argument I, the plain old I, as their key, make the corresponding value the result. And always be sure to pass along that memo by reference into your recursive method here. So that would mean right here, pass along the memo. So I have that shared data structure. And so just by adding this layer on top of our brute force, let's give that a test run. We should get a much better runtime here. Cool, and there we have it. Hey programmers, Alvin here. Right now let's go over the approach for this summing squares problem. So the first thing we'll want to do is review what a perfect square is. You can create a perfect square by just taking some positive number and multiplying it by itself. In other words, I can do 1 times 1 to give me 1, 2 times 2 to give me 4, 3 by 3 to give me 9, and 4 by 4 to give me 16, and so on. So in this problem, we're going to take in a number as input, and what we want to do is figure out the minimum perfect squares that sum up to our target number. So for this input of 12, the least number of perfect squares I can use would be doing 4 plus 4 plus 4. Notice that this is a valid perfect square sum because 4 is of course a perfect square. Another way that uses perfect squares to add up to 12 would be 9 plus 1 plus 1 plus 1. However, that would be a longer way. Right? I want to use the minimum number of perfect squares, and so here I should return the answer of 3. And the reason behind it is because I do 4 plus 4 plus 4, which is 3 perfect squares. All right, so how can we break down this problem? Let's step through the example as if our input was 10. I'm going to start at 10 at my root, and what I know I have to do is get this number to be smaller and smaller, because decreasing the size of our input would mean an easier and easier problem to solve. So what I have to do is subtract different perfect squares from this 10. So what I can do is subtract 1, that'll give me 9, or I could subtract 4, giving me 6, and finally I can subtract 9, giving me 1. Notice that there are no other perfect squares to try. The next perfect square would be 16, but that would be too large for my 10, so I don't need to go over it over here. Let's say I now wanted to expand this 9 node. I would get children like this, again branching for every perfect square that I can take out of that quantity, and so on and so forth. If we look at the right-hand side of my tree, I actually just discovered a way to create my input of 10. In other words, I can look at this path. Since this path terminates in a 0, that must mean that we have just found a way to sum up perfect squares such that we get 10. If I look at the numbers along this path, I'm really saying 9 plus 1. So let's expand this 5 node, as well as this 2 node, and we'll build the full tree for the subtree rooted in 6. That would look something like this. And so you can probably foresee that this tree grows very quickly. And so we're going to avoid drawing the left-hand side of the tree, although now we know the core pattern that we can use to generate it. So if I look at this subtree, I have a few different paths that terminate at 0. Right? I can look at this path, which represents another way I can create my input of 10, but I should obviously prefer a shorter path, right? If I count the number of edges within a path, that would tell me the number of perfect squares I use to accumulate that sum. And obviously the shortest path we should return here is 2, because we're using a 9 and a 1. But let's go through how we can actually code this one up. So as always, if I have this visualized as a tree, then I should be able to frame it as some recursion. So in my base case, if my input is 0, then what I should do is return 0. 0 is a great return value because what we're saying is to create 0, you need to sum up 0 different perfect squares. So I'm going to plug in that return value for all these leaf nodes. And as I return these values to their parents, what I have to do is add 1 to them always. That way I can start counting the number of edges. So if I look at the very bottom right now, the 0 returns, then I add 1 to it, then it returns upward, add 1 to it, and 1 more time to get over here. Notice that I have a 3 over the 3 node, which means that I need 3 perfect squares to create 3, which makes sense because you have to do 1 plus 1 plus 1. Let's say we return at this 4 node. Since this node's receiving 2 different values, what it should do is choose the smaller between the 2, right? Because this problem's asking us for the least number of perfect squares. So I need to minimize here. So I should prefer the 0. What I should also do is add 1 to it to count the edge. And so what I'm saying right now is there must be only 1 perfect square that I need to get a quantity of 4, which makes sense because 4 itself is a perfect square. So I should be able to notice any correctness even as I evaluate these subtrees. So we'll take some time to evaluate this further. Until finally at the 6th node we get a result of 3. And this 3 represents a few different paths we can take that are of minimal length. So I think by now you understand the logic we need to evaluate this tree. This tree is going to be a little large, so I won't step through the full example. We can already foresee the complexity of this though, right? Whenever I have a tree structure like this, I'm describing all the different recursive calls that I make. So if I'm able to figure out the number of nodes in this tree, that would tell me the time complexity that stems from the recursion. What I know is the height of this tree is definitely going to be n, right? Because the longest path from the root to a 0 would be just by taking a -1 again and again, right? So the height of this tree is going to be n. When it comes to the branching factor, it's actually dynamic. So given a node, we know that we branch for every perfect square that we can fit inside of it. We know that given a node n, there would be square root of n different perfect squares. So that'll tell us our total complexity. We'll say that the time complexity is going to be the square root of n raised to the nth power. Like usual, the branching factor of our tree is going to be the base of that exponent. In this problem, the base is no longer 2, right? We've been dealing with a lot of problems where we just have a base of 2. Now we have a branching factor that's based on the square root of that number. So that's why we say we have square root of n raised to the nth power. The exponent of n, of course, represents the number of levels in this tree or the height of the tree. In a similar way, the space complexity is just linear, O of n, because of the height of our tree. We know that we're going to need, at most, n stack frames in our deepest call stack. And like you could probably guess, this is actually going to be framed as a dynamic programming problem, right? What we can do is notice some overlapping subproblems looking at our tree. You can capture a few. I'll just point out this duplicate 5 node. And of course, as we grew our input larger and larger, you would have more and more overlap. So if you do things properly here and you implement memoization to capture the dynamic programming nature of this problem, what you should be able to do is bring it to some sort of a multilinear function. Overall, your time complexity would be n times the square root of n. And your space complexity would still be O of n. I'm sure you're wondering exactly how we implement this one, so maybe what you want to do is try to code it up on your own. If you get stuck, you can find me in the code walkthrough. I'll see you there. Hey programmers, Alvin from Shructi here. What I want to do is go over the Java walkthrough for the summing squares problem. So you definitely want to make sure you watch the approach video first, and we'll jump right in here. We want to solve this one using a brute force recursion and apply some memoization on top of it. So let's start with a base case here. Like we said in the approach video, we know we want to deal with an input that's very small, right? For us, we have integer inputs. So we'll just check if our number n is equal to 0. If our number n is equal to 0, then we want to return 0. Because we know that generally, our method should give us back the number representing the minimum number of squares used to build up our n, right? If your n is 0, that means you can use the empty sum, right? You can add up no perfect squares and you still get the correct answer of 0. So that's the logic behind our base case here. But now the recursive case is much trickier. We know we want to have the logic of subtracting out some perfect squares from n. That gives us a smaller and smaller argument. So I'm going to give myself a loop that just iterates over some possible squares. So what I can do here is I can iterate for int I equals 1. And I'm starting at 1 because I know that 1 is the smallest perfect square, right? So I might as well start there. And I'm going to iterate up to I less than or equal to the square root of n. And then hit every I in between, I plus equals 1. Cool. And that's because as I evaluate this loop, what I'm going to do is take my integer I, and I'm going to create a square number out of it. A square is just any number multiplied by itself. Nice. Notice that on the last iteration of this for loop, I know that I is going to be exactly the square root of n. So when I do I times I, I'm definitely going to get the full value of n. And this could be the biggest number we ever subtract out of our argument n here. Nice. And so with that out of the way, what we want to do is now build our recursive call. So I'm going to call summing squares, and I'm going to do n minus this choice of square that I have over here. We know that this recursive call is going to give us back the minimum number of squares required to sum up to this quantity, right? I'll call that my int num squares. However, if I wanted to figure out the number of squares to build up for our argument n, we need to add 1 to that subquantity, right? And that's because this 1 over here corresponds to the single square I have on line 9. Nice. And then I know I need to find the minimal sum. And so what I want to do is some min value logic here. So I'm going to do int, I'll say min squares. And here it would be nice if I can use some like infinity value, because I want to do min value logic overall. And so unfortunately, like integer type doesn't have a built-in infinity. And so what I'll do is I'll actually create this as my recursive helper. And so the main method will have the original signature. But my recursive method, I think I'll make it actually return double, because then I can start defaulting these values over here, right? So for line 13, I can make this default to double dot positive infinity. Then I get some safe comparison over here, right? So I can say things like, hey, if this number of squares is less than the min squares, and on the first iteration, this is guaranteed to be true because min squares is positive infinity, then you can go ahead and replace min squares with that value. Nice. Then after that for loop is done running, like you expect, we return whatever min squares is. And since we're storing positive infinity in this variable over here, this should be, of course, type double. which means that now our summing squares recursive method is returning a double, which is totally fine. However, when we actually call this helper method in our main method here, we know that this call to summing squares, that's actually going to give us a double. I want to just cast it into an int, like so. I'll pass along the same n here. Do bear in mind that right now, because these methods of summing squares, although I want to overload them, they will probably get a conflict here because they both take in the same types of arguments, and the return type is kind of ambiguous here. So just for now, I'm going to rename the helper method. I'll call it underscore summing squares. So that represents my recursive helper method. Nice. And so with that, let's give this a run. Here I'm just getting a little reference error for the typing. This should be positive infinity. And while I'm here, I also noticed that when I add 1 to the result of the recursive method here, that of course gives me back a double. Right, and that's because the method returns a double. I'm adding 1 to it, which should still give a double. Let's give that a test run. Nice, and this looks like our brute force recursion. It's starting to time out though on test case 06. So you know the drill. At this point we have our brute force. Let's add our memoization into it. So I'm going to start by importing the hash map, and I'll pass it along to my recursive method here. So it'll be a new hash map. I'll take it as argument here. So hash map. Keys are going to be just the numbers n, so integer. Corresponding value right now is going to be double. We'll call that my memo. And we'll add a base case like we always do if our argument n is in the memo. So if memo dot contains a key of n, then return memo dot get n, right? Return the stored value for it. Then I need to locate where I call my method recursively, which is over here. Be sure to share the memo. And then whenever you do your return value in the recursion, you want to store that result before you leave, right? So here I return min squares. I'll want to save that in a variable. I'll say result equals min squares. I'm going to still return that same old result, but before I leave, I store it in memo. So memo.put, use the original argument as the key, right? So I just use n here, make result the value. Nice. And so now that the overloaded version of this method has a different argument of hash map, it should be unambiguous now. So I'm going to actually change the name here just to summing squares, right? It's easily to identify now because there's 2 arguments for the recursive version, right? Only 1 argument for the main version here. So let's give that a test run. Always solving these dynamic programming problems in layers. Great, and there we have it. Hey programmers, Alvin here. Right now let's go over the approach for this counting change problem. So in this problem we're going to be given 2 arguments. We're going to be given a target amount as well as an array filled with some coin values. And what we want to do in this problem is return the number of ways that it's possible to make the amount given the coins in the array. And we can reuse a coin value as many times as we want. And so for this particular example, let's go through the ways we can make an amount of 4. One way would be to use just a bunch of 1-cent coins, or you could do a 3 plus a 1. You can also do a 2 plus a 2. And finally, you can use 1 2-cent coin and then 2 1-cent coins. And so that means there are 4 distinct ways to generate our amount. So let's trace through an algorithm we can use to solve this one. We'll start by structuring the different decisions we can make when it comes to building our amount of 4. So I'm going to use 4 at the root. And like we're used to, let's go ahead and branch for every coin value that we have available. In other words, what I could do is take a 1-cent coin, in which case I reduce my target amount from 4 to 3. Or I could take a 2-cent coin, in which case I have 2 cents remaining. Or I could take a 3-cent coin, in which case I have 1 cent remaining. Now you've seen this pattern a few times in the course already. If we built out the full tree, we'd end up with a structure like this. Notice that we terminate wherever we have 0, because that must mean we actually successfully built our target amount. We know that a 0 leaf would represent one of the ways to create our amount. Looks like we have too many zeros here. You're going to see that we have 7 zeros, but we said that there are only 4 ways to create our target amount. Let's start by interpreting one of these paths. So let's say I looked at this path. This path would represent me taking coins 1 plus 2 plus 1. And if I look at another path like this one in pink, this would represent the way of taking 2 plus 1 plus 1. If you look at those two paths, they actually represent the same coins, right? I'm using a single 2-cent coin and then two 1-cent coins. I just took them in a different order. And that's why we have a high count right now. We're actually counting duplicate ways. And so I don't want to return 7, although my tree says that. I should really return 4. So actually structuring our tree like this is not going to be the way to solve this problem. So what would be a better way? Well, we can still use our tree structure, so we're going to break this one down recursively, but we want to build it in a way where we don't have any duplicate paths, right? And so what we'll do is, starting at the root of our tree, we're going to make a decision for just a single type of coin. So at this top level of my tree, I'm only writing a decision for my 1-cent coins. And so for this coin with a value of 1, what I'm deciding on is how much of this coin to take. So I could take 0 1-cent coins, in which case my quantity that I'm targeting, my target amount, still stays at 4. Or I could take a single 1-cent coin, in which case my amount is now 3. If I take 2 1-cent coins, then now my amount is 2. And this would just carry further until I've exhausted all the possibilities for my differing quantities of 1-cent coins. So notice here along the edges of my tree, now I'm denoting the quantity of the coin I'm taking. And at this first level, I'm taking coin 1. What I can notice immediately is I already have a node that terminates at 0. So this must mean that represents one way I can generate my amount of 4. And what this path represents is really me taking 4 1-cent coins. And on the next level of the tree, what we'll want to do is make the same decisions, but for our 2-cent coins. So let's say I wanted to expand this node to 4. What I do is branch for different quantities for my coin value 2. So I can take 0 2-cent coins, 1 2-cent coins, or 2 2-cent coins. And that would give me 4, 2, and 0 as my remaining amount, respectively. So we're going to need some more room here. Our tree's getting a little wide. What I can do is notice this amount of 1. Since I'm trying to decide how many 2-cent coins to take, I actually can't take any 2-cent coins out of that amount. So this darkened node basically is going to be a dead end. So we can effectively ignore it. That's going to be true throughout this tree. Whenever we have an amount that we can no longer shrink, we actually don't need to expand that node anymore. And so let's reorganize things over here. Now let's expand this node of 3. And again, I'm branching for different quantities of 2-cent coins, right? So I can take a 0 2-cent coin, or I can take just 1 2-cent coin, in which case I result in an amount of 3 and an amount of 1. We'll carry this further for the other nodes at this level. Notice at this point, we've just encountered more 0 amounts, which means they represent other ways to create our target. So far we've counted 3 distinct ways to create our initial target amount of 4. Finally, at the bottom level, we choose different quantities for our coin value of 3. Notice that some of the leaves here don't terminate in a 0, which means that they don't represent valid ways to make my initial amount. What I can notice at the bottom level, though, is I have an additional 0. And this would actually give me all of the 4 different ways I can create my target amount. So the key pattern here is we want to make sure that up front we choose different quantities for a single coin value before moving to the next coin value altogether. What I don't want to do is flip back and forth between different coin values, because then I would end up looking at duplicate ways. If you think about how we have the tree structured now, we have a very short tree, right? This tree's height is just going to be the length of the coins array, because at every level of this tree, I'm choosing for a different coin value. So although my tree is very short, I actually have now a very wide tree, because now I'm iterating through differing quantities. It's like you can probably foresee, we can totally structure this problem like a dynamic programming problem, meaning you could spot duplicate subtrees here. Let's take into account the shape of our tree to come up with the complexity of this. So if we implement this wisely with some dynamic programming via some memoization, we should end up with a time complexity that's a multilinear. So just A times C, and a space complexity that's also A times C. We say that the time complexity is A times C because A is the width of the tree, and C is now the height of the tree. And in general, the number of nodes would be the height times the width. The space complexity is also going to be A times C because of the different keys we're going to need to put inside of our memo hash map. You're probably wondering exactly how we implement this and why the complexity is the way it is. And to do that, we're going to actually have to implement the code together. So at this point, you'll want to join me in the walkthrough videos. I'll see you there. Hey programmers, welcome back. What I want to do right now is go over the Java walkthrough for this counting change problem. So in this problem, like we said, it's going to be a variation of our, coin changey problems. And what we want to do is this time return a number of ways that we could generate our target amount. Like we said in the approach video, the thing to watch out for here is to make sure that you don't count any duplicate ways. And so the structure of this recursion is going to be a little bit different. I'm going to need an additional argument into my recursive method here. And so I'm going to define it down below. It's going to have mostly the same signature. I'm still going to take in the amount as well as all of the option of coins, but I'm also going to take in an index. I'll call it coin index. This is going to represent the index of the current coin that I'm going to consider, which means top level over here, when I call my recursive method, I'm going to give in the same old target amount. I'm going to give an initial coin index of 0, and of course pass along the original choice of coins here. And so what I get to do now with this coin index is now vary the quantity that I'm going to take the coin of the given index. And like we said in the approach video, we want to count the number of ways to generate the amount. And so recursively, I want to be reducing this amount over time toward my base case. In other words, once my target amount is 0, I have to think about how many different ways can I give back 0 cents. And the answer there is 1, right? There's exactly one way you can give back 0 cents, and that way is to do nothing, right? So this 1 represents me counting a valid way, right? There's one way to make 0 cents. Good. And then from there, what I want to do is now iterate over the possibilities. So I know that given this coin index, if I use it to access some value out of the coins list, I can do coins.get coin index. And I'm going to create a variable to store it. I'll call it int value. So this is the value of the current coin I'm considering. So if I take a look at the first example, in the event that coin index is 0, that means my value is 1. It's like a 1 cent coin. In the case that my coin index is 1, that means the value I get is 2. What I want to do is take varying amounts of this coin value. So I'm going to start iterating here. And this loop's going to be different from our previous coin problems in that we want to iterate over a different quantity, right? So I'm going to say int quantity. I have to think about what the lowest quantity of a coin I can take is. Well, the answer there is 0. You could take no instances of a coin. And I know I'm going to increase that quantity over time to go through the possibilities, but I have to think about how far I need to go. What I want to do is iterate this loop while the quantity times value is less than or equal to the target amount. So here I'm checking that my quantity times value is less than or equal to the amount because I don't want to overshoot my amount. So for example, let's say that right now my coin index is 1, right? So that means I'm looking at the element of 2 over here, right? If I do my quantity times value, I have to think about what's the most number of 2 cent coins I can take right now if my target amount is 4, right? Well, in the first iteration, this is going to be valid because I'm going to check if 0 times 2 is less than or equal to 4, right? And that's true. So I keep running the iterations. I'm going to check if 1 times 2 is less than or equal to 4. That's still true. Then I check if 2 times 2 is less than or equal to 4, and that's still true. But on the next iteration, when my quantity is 3, I'm going to do my 3 times 2, which is 6. And that's no longer less than or equal to my target amount of 4 because I don't want to take out 6 cents from my target of 4 cents. That would give me a negative quantity, right? So this condition ensures that I only iterate up to a valid point here. So what I want to do now is generate my sub amount. So I can do my int sub amount, and I'll make that equal to the original amount, but just minus the quantity times the value, right? I'm reducing the amount by the number of coins that I'm taking. Then from there, I have this reduced quantity I want to call recursively on counting change. I'll give in that sub amount. And because I just made a choice for how many instances of this coin index I'm going to take, what I want to do is now move to the next coin. So here's where I increment my coin index. So coin index plus 1. Right. Notice that this for loop is going to iterate through all the possibilities for my given coin index. And once I make a choice of that coin index, I can never go back to it. And so that's why I increment my coin index in the next recursive call. Along with that, I can pass along these same coins, right? That doesn't change. Awesome. Now I have to think about the logic of my problem here. I know that in the approach video, I wanted to have the effect of taking a total, right? I wanted to add up the sum of all of the branches through my tree. So I know that counting change is going to return an integer. That integer represents all of the ways that I can generate the sub amount. So what I want to do is take the grand total of that. So I'll say int total ways equals 0. And I'm going to add the results over here. Nice. So I'm getting the grand total number of ways. And after my for loop, I just want to return the total ways. Just a little typo over here. I should be saying total ways. So this looks mostly good, except I should consider also adding a base case regarding my coin index. In other words, what if it's the case that you actually exhaust all of your different options for your coin index, but your amount is still not 0? So let's say after this if statement, if I get past this if statement, I know my amount is not 0, right? And I also want to check, hey, if my coin index has no other options in it, in other words, if my coin index is greater than or equal to coins.size, then I have no more options, right? I know the last valid index of coins is coins.size minus 1. So if coin index is equal to coins.size, I know I don't have any more coins I can possibly take. So if you hit this case, you want to return 0, right? There's no possible ways to generate your amount from this point because you already chose all of your quantities for your different coin indices. Nice. The order of these conditions is really important, right? Because I have this if statement on line 13 after line 9, this is technically checking, all right, if my amount is not 0 and my coin index is out of bounds, right? And I'm able to accomplish that logically by the order of these two conditionals. So with that, let's give this a test run. This could be our initial brute force solution. Looks like we're going to time out. Nice, because we get that not so great exponential runtime here. And so like we're used to, we'll go ahead and memoize this, right? So I'm going to bring in my hash map, and I'll be sure to pass it in over here. So a new hash map. When it comes to designing the hash map over here, I have to think about what the keys need to be. As always, the keys need to be the changing arguments through my recursive method. And here it's actually interesting that 2 arguments change, right? My amount changes because I have some reduced subamount that I'm passing along, and also my coin index changes because from one call to the next, I would be increasing the coin index. And because those arguments change during the recursion, those are the ones I want to encode into my hash keys, right? So my keys here will actually be list of integer. I'll just make sure that that sublist or those sublists just contain a pair of amount and coin index, right? Corresponding return value is going to be integer, so integer will be the values of my map. I'll call that my memo. Nice. So what I'm saying is, I'll add another base case and I'll form my key. I'll just say list of integer. It's going to just be a list of the amount followed by the coin index. I'm going to use this entire pair as the keys of my memo. So I'm going to check if my memo contains a key of key, then I want to return its stored value. So return memo.get key, because that means I've seen this subproblem before, so I can return the previously saved subresult. And now what I want to do is make sure I pass along this memo by reference through the entire recursion. And also be sure to store your recursive return value into the memo before you leave. So that would be line 31 here. What I do is I can say memo.put. You always want to make the key for your stored value the original key that encodes the arguments, right? So amount and coin index are part of my key here. So I use that in my memo. And I store the total ways. And then just be sure to return the old value. So return total ways all the same, right? That shouldn't change. And so with this, let's go ahead and give this a test run. We should now be using our memo to solve this dynamic programming problem quite quickly. Let's see what we get. Awesome, and there we have it. Hey programmers, so you've reached the end of our dynamic programming crash course, but the learning doesn't stop here. If you head over to structy.net, you'll be able to practice some dynamic programming problems further. We have a full module on dynamic programming, a lot of the problems that you've covered in this video series for freeCodeCamp, but I have a lot more in store as well. So whether you're looking to really hone in on your skills of dynamic programming, or you want to cover and go through all the other topics we have featured on Structy, I recommend you head to structy.net. You're going to have access to video tutorials as well as animations with me for every single problem. I'll see you there.